Morning, everyone. Welcome to the second day of our conference, Hydrogen Fuel Transport Integration with the Whole Energy System. The second day is structured around the challenges in hydrogen combustion, distribution and storage. Just in case you weren't with us yesterday, I'm Tony Roskilly. I'm Professor of Energy Systems at Durham University and a Director of Durham Energy Institute. And I lead the Network H2, which is a national hydrogen fuel transportation research network plus funded by EPSRC. Please visit our net zero research website to find out more details about the research we fund and the dissemination activities we have done and will continue to organize. Over the course of today, we'll hear from academics and industrial leaders who are engaged with research and innovation challenges across the different forms of transportation, as well as in the developing the supply chain to support hydrogen transition. Thank you for joining us this morning. Today is organized in two sessions, morning and afternoon, and we are delighted to welcome speakers from industry to provide keynote presentations at the start of both. The academic papers delivered today provide a range of perspectives. Some of the research has been funded by the network and others has been undertaken by researchers working on sister projects. And we look forward to hearing a diverse approach, engagement and perspectives and findings, and hope that this will stimulate further ideas around hydrogen research and innovation. So without further ado, let's go on to the first session. And I would like to introduce our first keynote speaker. Dr. Naomi Allen joined the Aerospace Technology Institute as a senior technologist in the whole aircraft team in May 2019. She works on whole aircraft modeling and conceptual design and is responsible for developing the models and tools required to support the UK industry in research and technology developments for large commercial aircraft. Before joining the ATI, Naomi was most recently worked for Formula One Mercedes GP team, developing wind tunnel test capability and optical techniques. Prior to that, she worked in experimental and computational aerodynamics for Aircraft Research Association and Sterling Dynamics. Naomi has an MSc from Cranfield in aircraft engineering and a PhD on airflow sensor design from Durham University. Over to you, Naomi.
Thank you very much. It's a pleasure to be here. Thank you very much for inviting me. I'm just going to share my screen. So I've been invited to talk to you about challenges of hydrogen transportation. As you can tell from Tony's introduction, my background is very much in aerospace and aviation. So most of what I'm going to talk to you about is very much in that sphere, although some of the challenges that we're talking about here are applicable not just to one particular form of transportation, but many or even other industries entirely. So just to start off with a little bit about the Aerospace Technology Institute where I work, we are a part government and part industry funded organisation who are responsible for setting UK Aerospace's technology strategy for the next several years. We released our most recent strategy earlier this year called Destination Zero. And as you can tell from the name, that's very heavily focusing on how we achieve net zero in aviation by 2050. Part of that technology strategy is producing roadmaps, high-level roadmaps for the sorts of technologies that we need to be looking at. And these are split into ultra-efficient aircraft, which is what we call the next generation of kerosene-burning aircraft, zero carbon emissions aircraft, which may be burning hydrogen or other fuels or batteries, and also cross-cutting enabling technologies, which will be applicable to more than one type of aircraft. We also manage the funding that's available from the UK government for industrial research. So we fund projects which are in that space between TRL 3 to 6, trying to fill that funding valley of death that I'm sure you're all familiar with. And we look for projects which are well aligned with our strategy and which are developing technologies and delivering those technologies which are going to be required looking forward to 2050 for net zero. In addition to the standard funding that we manage, we also very recently had the Fly Zero project, which was looking at the potential for zero carbon aircraft. And much of what I'm going to be talking to you today about is drawn from the conclusions of that project, the Fly Zero project. We also do some sustainability modelling. So myself, I do the aircraft modelling side of things, but then we put the data that we derive from those aircraft models into a sustainability model to allow us to look at how the introduction of new aircraft with new technologies might affect the global carbon emissions from aviation. So this is one of the plots that we've produced recently to try and show where the contributions for reducing emissions will come from. The top line here is the emissions that we would expect to see out to 2050 if we don't do anything at all. If we just carry on with the current aircraft that we have, this is the sort of emissions that we would be expecting to see. The top sort of pinkish wedge there that you see is the degree of reduction that we expect to see through making it more efficient aircraft. So the next generation of kerosene-fueled aircraft, we expect to see this kind of level of improvement. The next wedge down represents the introduction from the mid-2030s of zero carbon aircraft. We'd expect those to be liquid hydrogen fueled. And as you can see, they have quite a big impact, but it takes a long time for new technologies in aviation to flow through. The replacement of the fleet is very slow. The life of an aircraft in the global fleet is 15 years or more generally. So even when new aircraft enter into service, it takes a very long time for their effects to be seen in aviation. We also expect to see some improvements in emissions due to improved operations, and also sustainable aviation fuel is going to give us a big improvement as well. However, we do believe that there will be limitations to the amount of SAF that can be derived from biomass. So therefore also power to liquid is going to be something that we're going to need to invest in. There are also market-based measures such as CORSIA, which will also have an impact in terms of reducing carbon emissions. But there is also quite a large chunk left there at the end where we are not entirely sure where those emissions reductions will be coming from. So there's definitely a lot of scope, even beyond what we're predicting will happen, which will either need to be filled by further offsets, market-based measures, or through synthetic SAF. So that's the picture. We firmly believe at the ATI that both ultra-efficient aircraft using SAF and zero carbon aircraft are going to be essential if we're going to be able to decarbonise aviation by 2050. And just a little bit more about the Fly Zero project. So this was a 12-month project. It ran a little long. It ended in March. It took place through 2021 and ended in March this year. And its brief was to look at the feasibility of zero carbon flight for large commercial aircraft. Now, obviously, a lot of people have done work on batteries, but the expectation is that those will only be relevant to fairly small aircraft. And people have been talking about hydrogen and other means, but we really wanted to investigate what the best options were. And they didn't look straight at hydrogen, they did evaluate other fuels as well. The project, because it was a fixed term, it drew secondees from a number of different companies across the UK in aviation, brought together over 100 engineers and other people working in aviation to really try and look at this, not just on a narrow basis of the aircraft design or anything like that, but looking at it much more broadly in terms of the operations, the market and economics, and trying to consider all the aspects of what it would mean in order to introduce zero carbon emission aircraft into the fleet. There were some key takeaways here from this project. One was that they found that green liquid hydrogen was going to be the future for zero carbon aircraft. And they did consider other fuels and sources of energy, but the most promising thing that they looked at was liquid hydrogen. They also looked at some aircraft concept designs. So they came up with concepts both for regional, narrow body and mid-size aircraft, so 3 different aircraft. And the largest of those aircraft carried 279 passengers and had a design range of 5,750 nautical miles. That's considerably larger than the conventional wisdom of what liquid hydrogen would be able to achieve. Much of the published literature out there suggests that you're limited to 1,000 or 2,000 nautical miles and smaller aircraft. but the Fly Zero project did find that it is potentially feasible to look at much larger aircraft. This mid-size concept, it would enable you to fly between any two airports on the globe with only one stop. So it's really enabling the possibility of zero carbon flight for across a very wide breadth of the flights that take place now. They also looked at multiple different fleet scenarios, so how you might introduce these aircraft, what order that you might introduce them in, and what impact that would have on the overall sustainability picture. And they've also produced roadmaps for the technology development, so what would actually be required in order to realise this vision of zero carbon flight. And most importantly, looking at the cross-cutting technologies and the enabling ecosystem, because this is not something that the aviation industry is going to be able to do in isolation. There are a lot of things which are going to need to be put in place from outside the industry. So it's very important that we understand these very early on. So I just wanted to go into a little bit more detail about the aircraft themselves. I'm going very lightly over quite a large number of different topics here, so no great detail, I'm afraid, on any of them. But the regional concept, this is probably one of the aircraft that looks more different from what we see flying today, principally because of the distributed propulsion that you see on the wings. This is an aircraft which uses fuel cells for its propulsion. So that's a new technology that we don't currently see flying today, although there are some projects currently in action looking at this on much smaller aircraft. This regional aircraft carries 75 passengers and has an 800 nautical mile design range. As you can see from the payload range diagram, it is much more restricted in terms of its range capability than the reference and baseline aircraft that the team looked at. But it does meet the design requirements that were set for this, which would capture a large number of the types of flights which are flown by this type of aircraft today. Some of the big challenges that the team found when they were looking at this aircraft was around water management from the hydrogen fuel cells, also the fuselage diameter. So carrying liquid hydrogen fuel tanks on board an aircraft drives you towards a larger diameter aircraft, larger diameter fuselage than you would typically see today in order to have an efficient gravimetric efficiency or a good gravimetric efficiency for the hydrogen fuel tanks. And obviously this creates more drag. So there is some work to be done looking at how we can optimize this. In terms of the aircraft size, the team, when they looked at this aircraft and developed it, they found that the energy usage for this aircraft was slightly higher than you would expect from an equivalent kerosene burning aircraft. And they think that that was probably because this aircraft is slightly above the optimum range for fuel cells. So there's some more work to be done looking at what is the optimum size of aircraft to be driven by fuel cells. And with this regional size, would we be better off with a hydrogen combustion concept? You can see here the fuel tanks are at the rear of the aircraft and it has the distributed propulsion. But other than that, it is in some ways a relatively conventional looking regional aircraft. So this is the narrow body concept that the Fly Zero team came up with. It has fairly similar TLAR's top level aircraft requirements to the current aircraft. So a passenger count of around 180, a 2,400 nautical mile design range, which is somewhat shorter than the design range that is currently set for equivalent aircraft such as the A320neo or Boeing 737 MAX. It's worth my pointing out that these aircraft designs, these concepts are not intended to necessarily represent the optimum solution for this size of aircraft using liquid hydrogen. The team were trying to look at different technologies and understand the implications of integrating different types of technologies on the aircraft. And so therefore, they've taken quite different approaches to the three different aircraft. On this narrow body concept, the engines are mounted on the rear fuselage. And this has some real benefits in terms of the fuel systems and the proximity to the fuel tanks, which are carried in the rear of the fuselage. And it does mean that there is a high tail, a T-tail on this aircraft. This aircraft is using hydrogen combustion in contrast with the regional concept, which use fuel cells. And you'll notice looking at it that this is a 3 lifting surface configuration. So in addition to the standard wings and tailplane, you've also got canards at the front of the aircraft. This is a necessary addition in order to counteract the CG issues which are associated with carrying your fuel and having your engines at the rear of the aircraft. So this is something that the team found not just on the narrow body aircraft, but also on some of the other aircraft as well, that understanding the balance and the stability of the aircraft is crucial in being able to come up with a feasible design. I think this is something that there's still more work to be done on in order to find the optimum way of managing these issues around CG and stability, but it does depend somewhat on how you lay out your aircraft and the architecture. So I think we need to do more work looking at this and trying to understand what the implications are of different layouts and architectures on the stability, and whether there are more gains to be had through taking a different approach. In addition to the obvious changes to this aircraft configuration, it's also worth noting that this aircraft has a dry wing. Most aircraft flying today have the fuel stored in the wings, but given the volume of liquid hydrogen required on an aircraft, that's not feasible any longer. And also the geometry of the fuel tanks that you'll be able to fit in the wings is very suboptimal for liquid hydrogen, where you want as close to a spherical tank as possible. So this drives you towards a dry wing design, but this is going to require quite a considerable amount of work in terms of realizing these aircraft to try and understand what that means, what benefits that might bring in terms of the aerodynamic external surface design of the wing, but also in terms of the structures and the systems which are on the wing's control surfaces and so on. The eagle-eyed amongst you may have noted that the front end of the fuselage here is slightly narrower than the rear end of the fuselage. And this is an attempt to try and accommodate the fact that using liquid hydrogen fuel tanks, because of the volume constraints and the cooling requirements, is trying to drive you to a wider diameter. So the intent of this design is to try and maximize laminar flow on the fuselage. But this is something that's currently at a very early stage of concept and needs a considerable amount of work done to it before it could actually make it into an in-service aircraft. This aircraft also has slightly higher aspect ratio wings than the current fleet of narrow-body aircraft, and as a result would require folding wingtips on the ground, such as seen on the 787 or equivalent. You can see from the payload range for this diagram, again, the range is somewhat shorter, but it does capture the vast majority of flights that are carried out by the narrow-body aircraft, where relatively few flights actually use the full capability of the aircraft in terms of range. And finally, the mid-size concept. So this is a particularly interesting proposition for aviation because, as I said before, we weren't expecting at the outset of the FlyZero project that it would be feasible to use liquid hydrogen on an aircraft of this size, but it really opens up a lot more scope in terms of the routes that can be flown and the proportion of CO2 emissions that can be reduced through zero carbon emission aircraft, because the larger aircraft, because of their longer range and longer capacity, actually generate a significantly higher proportion of the emissions relative to the much smaller aircraft. Interesting thing to note on this aircraft is the green tank that you can see just in front of the wings at the bottom of the fuselage. They call this a delta hydrogen tank. And this is needed in order to get the amount of hydrogen on board that you would need for the longer ranges. However, there is definitely some work to be done around certification and the regulations, because this is not a configuration that would currently be viable with the current set of regulations. However, I think that there is some scope for looking at how these can be provided without obviously reducing safety. It's critical that with our zero carbon emission aircraft that safety is maintained or improved. Some of the challenges to note on this particular aircraft around the engine design. The design of a hydrogen combustion engine tends to drive you towards a lower bypass ratio because of the increased fuel efficiency that you see from going to a higher bypass ratio, because the weight of the fuel is relatively low, is entirely offset by the weight of the engine itself going to a higher bypass ratio. And this means that you tend to see your optimum at a much lower bypass ratio than we would see on a kerosene burning aircraft. The fuel system integration is also a big challenge on this type of aircraft, where the fuel tanks are a long way away from the engines potentially. The integration for all of that, while maintaining safety with pipes and fuel systems running alongside the passenger cabin, is something that would need to be looked at. So there are a lot of challenges associated with so many of these aspects of the aircraft design. This is just one of the roadmaps that I've taken from one of the FlyZero reports, looking at the roadmap for liquid hydrogen combustion. So there is an equivalent roadmap also for using fuel cells for propulsion. The there are a lot of bits. It's not even with just thinking about the hydrogen combustion. In order to get to flight test, it's not just about the propulsion system, but there are also a significant number of technology bricks which need to be looked at, both in terms of the systems and the structures. And all of these need to be developed in parallel and all come together in order for us to be able to flight test the liquid hydrogen combustion solution. There's a lot of working parts here. There's a lot of things which are new to the aviation industry, some of them already much more developed in other industries. And so I think we need to maximize the spillover from other industries into aviation where we can in order to accelerate the adoption of these technologies. But you can see here that there are a lot of things that all need to be brought together if we are going to get these aircraft into service. Moving away from the aircraft themselves, it's no good developing the best hydrogen burning aircraft that we can if the infrastructure isn't there to support it. And there are a lot of things which are going to need to come together. Something that is still at the early stages of thinking about how we're going to realise this is in terms of how we get the hydrogen fuel to the aircraft. There are a number of different options of how we can do this, assuming that the best sustainable option is to use green hydrogen in these aircraft. Then these need to be produced from renewable electricity through electrolysis. And then because we need liquid hydrogen for aircraft, we need gaseous hydrogen, doesn't give us the energy density that we require. There's also the liquefaction process that needs to be taken into consideration. And there are different considerations depending on the size of the aircraft and the types of renewable electricity which are available in different countries and different airports and different regions of how this could be configured. So one option that we're showing here is that all of the production of the liquid hydrogen can be done off-site and then transported either via pipe, which is probably only efficient over relatively short distances, or through transportation through trucks or equivalent to the hydrogen, where it is then stored and then conveyed to the aircraft. There's also the option to create the hydrogen in gaseous form off-site, but then carry out the liquefaction on-site at the airport before storage or going straight to the aircraft. And the third option is to do all of this at the airport. So go through the electrolysis process to create the green hydrogen, and the liquefaction and storage is all on site. The plot that I'm showing down in the right-hand corner sort of tries to indicate the size of these different options, the land use and the space that is required to realise this. So for small, medium and large aircraft, I hope you can see these. So for the three different scenarios, the thick grey bar that you can see there at the bottom is intended to represent roughly the size of a large airport's passenger terminal building, just to give you some context for the size of land that would be required for these different options. So you can see that for a large airport, there is a significant land use associated with liquid hydrogen use, regardless of where the liquid hydrogen is produced, obviously increasing if the entire production process is on site. For smaller airports, the land use is much less, but however, it is also more feasible for smaller aircraft to go to transport their liquid hydrogen on site through tankers. For large aircraft, with long-range aircraft using liquid hydrogen, there's a significant requirement for a high number of tankers if you're tankering all of your liquid hydrogen to the airport. And sort of going one step closer to the aircraft, one big thing that needs thinking about with using liquid hydrogen aircraft is the refueling. There are currently regulations in place governing what can be done during kerosene refueling and how that is carried out. And some of those are not necessarily directly appropriate to using liquid hydrogen. There are, since the safety zone that you need around where the hydrogen fueling is taking place is quite significant. And this could have a real impact on turnaround times for aircraft, which has a big implication for both airlines and airports if no other concurrent tasks can be carried out while the aircraft is being fueled. So you can see here that depending on whether you can do no simultaneous activity, some simultaneous activity, or you can carry on with all of the other baggage loading, passenger loading, and other aspects of supplying the aircraft simultaneously, it has a really big impact, particularly for the larger aircraft in terms of the time it takes to ready the aircraft for a new flight. So at the moment, 20-metre safety zone is considered appropriate around a liquid hydrogen fueling of this type. However, there is some discussion going on at the moment about whether that could be reduced to an 8-metre safety zone, and that has some quite significant implications in terms of the utilisation of the aircraft and the efficiency at the airport. But this is something that's going to need to be proven as safe before we can proceed. One of the biggest challenges around using liquid hydrogen on aircraft is around the fuel tank design and the fuel tank management. And it's no good just looking at the fuel tank in flight. The way aircraft are operated, they're frequently fueled well in advance of their flight, and they may still have fuel on board when they land, which may remain in the tanks for a considerable time thereafter. So the Fly Zero team were looking at the dormancy of the tanks. They were assuming a 10-hour dormancy period before the flight, followed by the flight period itself, and then a 3-hour dormancy period after the flight. And this actually drives the requirements around the tanks quite significantly, in terms of the pressures and in order to avoid leakage. Leaking hydrogen fuel has some quite significant impacts in climate change in and of itself. So it's obviously venting is to be avoided if at all possible. And so therefore we really need to think about exactly how this can best be achieved. At the moment, people are looking at sort of metal fuel tanks, but also looking to the future towards composite fuel tanks and how we can achieve a good gravimetric efficiency, which is really critical for aviation. It's perhaps less important in the automotive industry and some other industries which may use liquid hydrogen or gaseous hydrogen. But for aircraft, in terms of efficiency, weight is king. You need to drive the weight out of the aircraft, and that requires you to have a good gravimetric efficiency, where the gravimetric efficiency is effectively the mass of the fuel divided by the mass of the fuel and the fuel tank itself. So this is going to be one of the biggest challenges for aviation in terms of using liquid hydrogen, and it is something that's relatively unique to the aviation industry. It's by far more important here than it is in other industries. So it's something we're going to have to look at. So just thinking about climate impact and what would the introduction of these aircraft mean in terms of the climate? So one thing that here on the right-hand side, you can see the breakdown that we've got between different types of aircraft. So we've got the 3 different concepts. You can see that the regional concept actually accounts for relatively little of the aviation emissions due to their shorter range. The narrow-body aircraft currently flying actually emit just over half of the CO2 emissions that we see, and the wide-body aircraft also emit a significant proportion. But it's not just about CO2. So using liquid hydrogen has potentially some other benefits in terms of the fuel cells that can eliminate NOx emissions as well. But with hydrogen combustion, we're still going to see NOx emissions. There's also things associated with water vapor and a high level of uncertainty in terms of the climate impact of contrails. It's something we have a lot of confidence in our ability to predict the level of CO2 emissions, but in terms of contrails, that's still relatively unknown, and we're reliant on the climate scientists really helping us to understand that in the aviation industry. You can see the plot here shows the different types of emissions, all of which have a climate impact. Some of these are a high level of uncertainty, as I just said, but you can see that on the right-hand side of that plot, where we're looking at the hydrogen gas turbine, hydrogen fuel cell, the CO2 emissions in flight are entirely eliminated. There are still CO2 emissions surrounding the fuel production potentially, and that is something else that we need to look at. But the remaining large proportion of the potential climate impact of these aircraft is going to be around contrails. And so that's somewhere that we're going to have to put some effort into understanding how we can reduce that impact. So right at the start, I talked about the Fly Zero team looking at the kind of fleet scenarios that they could consider. And the general way of working in aviation is that things tend to get introduced on smaller aircraft first and then scaled up towards larger aircraft and de-risking the new technologies in the process. So they may start on very small aircraft, sub-regional, then regional, moving up through the classes of aircraft. If you look at the top graph I've got there, that sort of indicates the level of climate change impact we could expect to see between 2030 and 2060. And it does reduce the carbon emissions by a good degree. There are still quite a high level of other emissions. What we then looked at was, what if we did this the other way? We know that the larger aircraft have a much higher level of climate impact rather than the smaller aircraft. So rather than going for the conventional approach of introducing new technologies on the regional aircraft first and then scaling up to the narrow body and mid-size, what would happen if we looked at really accelerating the technology development and implementation and trying to bring to market a mid-size hydrogen aircraft first, followed by the narrow body aircraft with the regional aircraft coming in behind. And you can see from the plot that shows that kind of scenario has a much bigger impact on reducing the overall climate impact from aviation. So this is, in terms of pure terms of sustainability, this is a very attractive option, but it does have a lot of challenges associated with reducing the risks adequately if you're going to be able to bring a large aircraft to market with very radical new technologies. So it's important that we put our efforts into trying to accelerate these technologies to make this feasible, but we also need to recognise the high risks associated with it and be realistic about whether this is a viable option. And finally, it's not just all about the technologies. This is also about the people that we need. I'm showing here, it's probably too small for you to read the details of, but this is trying to show the skills and the people that we're going to need if we're going to realise these technologies in aviation. This is in the short term, from the 0 to 5 years, this particular chart. We have another one for the longer term. So this one is largely looking at, in terms of the materials that are going to be required, so that these things we need to understand very early, and also around the design and validation, whereas the longer term looking equivalent chart is looking more in terms of the manufacturing and some of those kind of aspects of these aircraft. So there are skills required across all of the aspects of aircraft design. So around propulsion, both gas turbines, it's sort of, relatively similar to what we currently have, but also entirely new things around fuel cells, which we don't currently have on in-service aircraft. There's also a lot to be done around the systems, particularly the fuel systems, but other systems as well, and thermal management, and also in the structures, things like the dry wing. And it's there are new skills that we need to learn, but there are also an increase in the number of people that we need with these skills. And this is across the full spectrum of people working within engineering. So technicians and operators, but also engineers, and also researchers who are doing the fundamental research and the industrial research, which is going to be needed to bring these technologies up through the TRL levels. So just to conclude, I would just say that this is very much a view of the world in September 2022. Things are changing very rapidly. It may be that in 6 months' time, if you ask me this again, we may have identified new things, which are some more important challenges that we haven't got to at this point. And it may be that some things, sufficient work has been done in order to de-risk them, and that it's no longer considered to be a sort of key thing that we need to understand if we're going to realise these aircraft. So it's a time of very rapid change in the aerospace and aviation industry, and we need to try and keep current with what's going on. The FlyZero project showed us that really if our main focus is around decarbonising aviation, then accelerating large liquid hydrogen aircraft into service is the best way to reduce emissions rapidly. We need to be making technology breakthroughs in 6 key areas. Some of those are around the propulsion systems, but also a lot around the other associated systems, such as thermal management that I mentioned previously, and also electrical propulsion systems, your fuel cells. How do you actually turn that into propulsive power? And also the aerodynamic structures, so things like the dry wings. If we're going to get these aircraft into service in the early to mid 2030s, then these critical technologies are going to need to reach TRL 5 to 6 by 2025. I also just wanted to point out, this is not something the aviation aerospace industry can do on its own. Climate science is going to be fundamental to this, and also in terms of the energy industry around the fuel production side of things, this is something that we're really going to need to work together with other industries on. And we're going to need, in concert with developing these technologies, we're going to be needing to talk to the regulatory authorities, both in terms of health and safety and in terms of the aircraft certification side, to make sure that when we are ready to introduce a new aircraft into service, the regulatory environment is also ready for us to be able to do that. So thank you very much for your attention. I hope you found it interesting. I would direct you, if you want to look into more of this stuff that I've been talking about, you could go to our website. There are a large number of publicly available reports from the FlyZero project, which go into much greater detail than I've been able to today. And we also have other reports on there around the integration of hydrogen into airports and so on, as well as our technology strategy. So thank you very much.
Thanks very much, Naomi. That's a very interesting and thought-provoking presentation. Let's move on to our next speaker. Fangyu Zhang is studying for a PhD at the University of Birmingham, and her research is on ammonia and hydrogen combustion. She previously studied at Newcastle University and is also gained her bachelor's degree from Shanghai Maritime University.
Thank you for introducing me. Good morning, everyone. I am Fangyu Zhang, a PhD student, and I would like to share our work investigation on flame stability limits of ammonia hydrogen and ammonia methane diffusion combustion. I will give a brief introduction and talk about the experimental setup, results, discussion part, and at the end, give a brief summary of the conclusions. In order to mitigate the climate change and achieve the net zero target, as mentioned a lot in the presentations yesterday, finding an alternative fuel for heavy transports is essential. Ammonia has been considered as a potential hydrogen carrier. It contains no carbon, and it has high gravimetric and volumetric hydrogen density. The industry of ammonia production, storage, transportation, and utilization is well established and reliable. Currently, the research on the sustainable and the renewable ammonia production technologies, such as using wind energy, hydropower, is very popular and will be applied in the near future to produce greener ammonia. And of course, there are some challenges of using ammonia as fuel. Ammonia has really low laminar flame speed, 7 centimeters per second. We can see in the table that compared to hydrogen, it has laminar flame speed is nearly 300 centimeters per second, and methane is 37 centimeters per second. And also ammonia has a narrow flammable range, which makes it really difficult to stabilize the flame. Ammonia doesn't contain the carbon, so the heat release rate is low. And if we are using ammonia as a fuel, since ammonia contains nitrogen atoms, NOx emissions will be expected at the exhaust. And so in this study, ammonia will be blended with hydrogen and methane. Both hydrogen and methane has been proved to effectively increase the flame speed, ammonia flame speed, and improve the heating value. Moreover, hydrogen can be obtained from the ammonia cracking, so there's no additional tank required on board when we are using ammonia hydrogen blends. For ammonia methane blends, it can significantly reduce the reinvest cost for the engine modification. So in my study, the flame stability and thermal performance of ammonia hydrogen and ammonia methane diffusion flames is investigated to provide experimental basis for the development of low carbon engines. Smaller enhanced combustor test rig is established. Blow-off limits are explored in relation to hydrogen or methane blending ratios, inlet temperature, and the flow rates. Thermal performance, including inner wall temperature along the combustion chamber and outlet temperature, are studied in terms of global equivalence ratios, hydrogen or methane blending ratios, and the inlet temperature. So here the slide shows information about the combustion chamber. The inner chamber is 150 millimeter in diameter and 310 millimeter in length. The chamber has two detachable quartz gas windows. The swallow is utilized for the air inlets to circulate the hot combustion gas, hot combustion products from downstream to upstream, and increase the mixing ratio with the incoming fuel and air, and preheat the unburnt gases at the upstream. And the fuel enters the combustor through a fuel nozzle, which is surrounded by the swallow. And the fuel nozzle has 8 holes in 2 millimeter diameter with an injection angle of 45 degrees. And on top of the chamber, there are 5 probes available for measuring the inner wall temperature. This is a schematic diagram of the test rig. The flow rate of ammonia, hydrogen, and methane are adjusted by its individual mass flow rate controller. Ammonia and the hydrogen, or ammonia and methane, will be mixed in the fuel mixer before entering the combustor. On the other side, air is compressed in the air compressor and adjusted by its own mass flow controller. Two separate external temperature controller utilized to control the inlet temperature of air and the fuel mixture. Along the combustion chamber, there are 5 R-type thermocouples used to measure the inner wall temperature, and the outlet temperature is measured by another R-type thermocouple at the exhaust. All of the exhaust gases will be analyzed by a Horiba multi-gas analyzer and a gas chromatography in the next step. So in terms of the flame stability, we are measuring the blow-off limits. For determining the blow-off limits, the air flow rate is increased slowly by around 2% every 20 seconds, while the fuel flow rate is maintained constant until blow-off happens. The global equivalence ratio is accordingly calculated based on the air flow rate. The inlet temperature of air and fuel varies from temperature to around 500 Kelvin. Hydrogen blending ratios vary from 0.0 to 0.4 with a step of 0.1. And methane blending ratio varies from 0.2 to 1.0. The input thermal power is calculated based on the low heating value of the fuel mixture. On the right-hand side, the formula shows input thermal power calculated based on the ammonia hydrogen mixture. The effect of the 8 and 16 kilowatts of input thermal power was on the flame stability was investigated. To obtain the temperature profile, the input thermal power is assumed as 8 kilowatts, and the inner wall temperature profile was collected from 5 thermocouples at the position from 4 to 232 millimeter from the burner. The combustion outlet temperature was collected with a probe inserted into the central line of the exhaust pipe. For each case, the temperature was measured for at least 45 minutes, and the temperature change is less than 20%, and then we see it is stable. The factors of inlet temperature of air and fuel, hydrogen or methane blending ratios are studied. So here's some results for the flame stability. On the left-hand side, the figure shows the flame stability of ammonia hydrogen diffusion flames under the room temperature. When the hydrogen blending ratio was 0.2 and above, the flame was observed at the input thermal power of 8 kilowatts. And when the thermal power was kept at 16 kilowatts, when only the flame was stabilized only when the hydrogen blending ratio is 0.4. Can be explained by the fact that when the thermal power is increasing to 16 kilowatts, the mass flow rate of the input gases are doubled, and the facility of the inlet gases are also enhanced, resulting in the flame being pushed away from the burner before the gas flow is recirculated to the burner. Moreover, the rich blow-off limits are increased while the lean blow-off limits are decreased even more, indicating that the hydrogen addition is more pronounced for stabilized diffusion ammonia hydrogen flame in lean fuel conditions. The right figure shows the flame stability of ammonia methane diffusion flames under the room temperature at the thermal power of 8 kilowatts. Flame was observed when the methane blending ratio was 0.5 and above. And when methane is dominant in the fuel mixture, for example, 20% of ammonia with 80% of methane flame, the blow-off behavior is similar as that in the pure methane flame. As more methane is blended with ammonia, the reach blow-off limits are significantly increased. In this slide, the figure shows flame stability under the inlet temperature from room temperature to 400 Kelvin and to around 500 Kelvin. As we all know that an increase in the inlet temperature improves the chemical reaction rate and the burning rate, so that the flame stability should be enhanced. And it is found that increasing the inlet temperature improves the reach blow-off limits considerably among all three types of flames, while the effect on the lean blow-off limits is not very obvious. It can be explained by the fact that ammonia has a low flame speed and it requires a high ignition energy to ignite and maintain the flame. So it has a greater impact on the reach blow-off limits, while since ammonia flame is burning steadily, so it has less impact on the lean blow-off limits. It is found that diffusion, 60% of ammonia, 40% of hydrogen flame has the widest stable range of the three flames. Although the lean blow-off limits for this type of flame under all conditions are extendable as the airflow rates reach the facility's limits. In terms of the inner wall temperature, the peak temperature was obtained close to the middle position of the combustor, and the inner wall temperature dropped after the middle point. We can see from the direct image that the hydrogen blending ratio has a great impact on the flame length. Consequently, the hydrogen blending ratio has a great impact on the inner wall temperature. The flame length with less hydrogen blending ratio was longer, resulting in the highest inner wall temperature occurred in the downstream. And for the methane ammonia flames, methane blending ratio has little effect on the diffusion flame length. The highest inner wall temperature occurred at 61 to 180 millimeter from the combustor. With more methane blending with ammonia, the inner wall temperature is increased. The increase rate can go up to 11.5%. From the previous studies, it is found that the highest temperature, ammonia flame temperature reaches highest when the equivalence ratio is around 1.0. So in this study, the equivalence ratio of 0.9, 1.0, 1.1 is studied. And under the room temperature, we can see that the maximum inner wall temperature collected from these three types of flames reached around 1,000 Kelvin. The combustor inner wall temperature of 30% of ammonia with 70% of methane increased slower than that of methane due to the low heat release rate of ammonia and the slow ammonia oxidation. However, the peak temperature collected in the middle of the combustor is similar. And with 30% of ammonia, 70% of methane flames, the inner wall temperature reached highest at the global equivalence ratio of 1.0 and 1.1, with 60% of ammonia, 40% of hydrogen flames. The inner wall temperature achieved highest at the global equivalence ratio of 1.0. Preheating the inlet temperature also improves the flame temperature in the flame zone. So for both flames under the room temperature, the inner wall temperature kept rising up to 180 millimeter from the combustor, while it kept rising up to 61 millimeter at 400 Kelvin of inlet temperature. Since there's not much difference we found in the flame length, this phenomenon is most likely due to the wall heat loss. And when the inlet temperature increases from room temperature to 400 Kelvin, the increase rate is up to 14.5% in diffusion ammonia hydrogen flame, while it is up to 14.7% increase rate in the diffusion ammonia methane flame. So we come to the outlet temperature. Combustor outlet temperature is very important as there's a close relationship between the outlet temperature and the exhaust emission concentrations. For example, one of the common NOx formation process is through the thermal NOx, which will be expected to increase when the temperature rises. And we can see from the figures that wall heat loss played a very important role in the combustor outlet temperature, because hydrogen addition and the methane addition both increase the ammonia flame temperature, but we can see that outlet temperature decreases when the hydrogen blending ratio increases, and when the methane blending ratio increases, the outlet temperature seems to be constant. And as we mentioned in the previous slide, that preheating the inlet temperature also increases the flame temperature. But we found that when inlet temperature rises, the outlet temperature in 60% of ammonia, 40% of hydrogen flame increases, but decreases in the 30% of ammonia and 70% of methane flame. So we can say it is worth to investigate more about the effect of the wall heat loss and compare the results in the simulation with an adiabatic wall to get more information. But the current results are also very, very important once we have the emission results in the lab. Here are some conclusions. At the room temperature, diffusion ammonia flame was observed when the hydrogen blending ratio was above 0.2, or when the methane blending ratio was above 0.5. Hydrogen addition is more pronounced for stabilized diffusion ammonia hydrogen flame in lean fuel conditions at the room temperature, while methane addition has greater impact on the reach blow-off limits. And it is found increasing the inlet temperature improves the reach blow-off limits considerably in terms of pure methane, or 40% of ammonia, 60% of methane, 60% of ammonia, 40% of hydrogen flames. The flame length with less hydrogen blending ratio was longer, resulting in the highest inner wall temperature occurred in the downstream, and the methane blending ratios has little effect on the flame length. With 30% of ammonia, 70% of methane flames, the inner wall temperature achieved highest at the global equivalence ratio of 1.0 and 1.1. And with 60% of ammonia, 40% of hydrogen flames, the inner wall temperature achieved highest at the global equivalence ratio of 1.0. Wall heat loss played a very important role in combustor outlet temperature. It is worth investigating further once the emission results are obtained in the lab. Thank you very much for your time, and here's all my presentations. Thank you.
Thank you very much, Fangyu, for a very comprehensive and interesting presentation. We will come to questions. Any questions for Fangyu at the end of the next presentation, which is going to be given by Dr. Penny Atkins from Brighton University. Penny is a principal lecturer in the School of Architecture, Technology and Engineering. She has a keen interest in the future sustainability of fuels and society in relation to the transport sector. coupled with research into low emissions, efficient combustion systems. Recent project work includes near zero emission hydrogen engines, investigation of the impact of hydrogen injection into the gas grid on heavy duty vehicles, and also the cost of ownership modelling of heavy duty transport. Over to you, Penny.
Thanks very much, Tony. Great to be here, and it's a really interesting day. Actually, it's great to see the work that's going on to bring hydrogen transport to reality. So I'm going to talk today, as Tony said, I've been working on hydrogen engines to support decarbonisation for heavy duty. So I'm going to talk a little bit about the background for that work, and then share some of the work that I've been doing with Ricardo and Hariba. So the work is very much a joint effort. So you'll see on the front slide my collaborators. So there's a team at University of Brighton, but then also at Ricardo UK, who have been supporting both technically and financially, and then Hariba, who've been supplying a hydrogen analyzer, which meant we've been able to look at the exhaust emissions for this hydrogen engine. So it's been a really interesting piece of work, which I'll share some of the results in a moment. So to start with, just an introduction to our research group. At Brighton, we've been working on low emissions combustion for many years with a range of industrial collaborators. So we started off looking at diesel, looking at soot, moved on to NOx. And then in recent years, as transport technologies become more diverse, we've started to look at things like cryogenic sprays, waste heat recovery, but really over the last few years, our focus has been very much on hydrogen, looking at hydrogen dual fuel with diesel and methane, but also pure hydrogen combustion, which is what I'll talk about today. So to look a little bit about the background to this work, for heavy duty on-road transport, there are very high energy needs. So the trucks run at high power and high for long ranges. So that means that the electrification can be difficult. So just a couple of examples, and I'll have used the same caveat that was used in the keynote, that things move on quickly. So, you know, things change, but I think the basic principles that I'll talk about here are true, in as much as if we're looking at electrifying an urban application, we might want a 200 to 300 kilowatt hour battery, which might cost you somewhere in the region of 20 to 30,000 pounds. So it's going to add significant cost to the vehicle in an industry where cost of ownership is all important, as profit margins are really very slim. Looking at long haul applications, we might think about using overhead charging. So if we were to assume that we had 10 trucks in a kilometre of road doing about 100 kilowatts, using about 100 kilowatts of power, then we might want 1 megawatt per kilometre. Now, the wind farm off the coast near Brighton University, Rampion Wind Farm, it's got 116 turbines, but that produces 400 megawatts peak, which would be enough for 400 kilometres of road with 10 trucks per kilometre. So the scale of electricity generation and also distribution is significant if we want to electrify trucks. And the picture is similar for off-highway, but you've got the added bonus in this sector that you have harsh environments. So the machines are working in applications like mining and agriculture, where it's dusty, it's dirty, it's hot. So the vehicles have very difficult durability requirements, and they have limited refueling options. So they may be in remote locations. So a whole range of challenges, which mean that decarbonisation is difficult in these sectors. So if we look at the two basic options we have, first of all, for any kind of decarbonisation, we need to reduce onboard energy consumption. We're looking at improving powertrain efficiency and reducing vehicle losses. For any kind of technology, we need to do that. But then we also need to decarbonise the energy source if we're going to reach net zero. So the keynote today talked about some of the options around liquid and gaseous renewable fuels. So we could use biofuels or synthetic fuels. And the potential for drop-in fuels is really attractive because you can provide decarbonisation in the short term. But the availability of these fuels is challenging, and applications like aviation, where the options are relatively more limited, may well have priority over those fuels. So hydrogen has been gaining much popularity for decarbonising these applications, and there've been a range of trials to demonstrate the technologies. So the good thing about hydrogen is it gives you potential for zero tailpipe emissions. You can refuel quickly, and you can have increased range compared to BEV. So, for example, fuel cell passenger cars, which are available, might give you a range of 700 kilometres rather than the 200 or 300 miles that you might get with a BEV at the moment. So hydrogen seems like an attractive option. Popularly at the moment, though, fuel cell is seen as the solution, particularly for on-road. But hydrogen engines may provide a good alternative, and particularly if you look at time to market. This roadmap from APC showed that for long-range applications, it was considered that cost-competitive fuel cells may not be on the market till 2030 or 2040. And if we're going to meet goals to decarbonise really quickly to prevent climate change, this may be too long. So hydrogen engines could offer a relatively short-term option, an alternative to PEM fuel cells, which could accelerate the uptake of hydrogen in this sector. So why could we do this more quickly? Well, the diagram on this page shows, actually it's a biomethane engine, but very similar to a hydrogen engine, and it's showing that essentially a hydrogen heavy-duty engine is pretty similar to a diesel heavy-duty engine, but with some changes because of the different combustion properties of hydrogen. So BMW have offered a 7 Series hydrogen powered engine in 2005, and there's been an awful lot of research and development in this technology over the last few years in Japan, China and Europe. And there's an industry view that the technology could be on the market by 2025, if not sooner. JCB showing some ambitious plans to have technology on the market maybe by 2023. So it's a technology that's really gaining momentum. So if you look at the efficiency of hydrogen engines compared to fuel cells, you'll see that so the blue lines on this plot show the hydrogen fuel cell efficiency, and the green lines show hydrogen engine efficiency. And the solid lines for those graphs are showing what we think the 2035 stack and engine efficiency could be. So this is almost the ideal efficiency. The dotted lines under those are showing the traction efficiency. So in other words, the efficiency to the wheels for both fuel cell and engine. So if we compare the green and the blue lines, you'll see that although the blue lines are more efficient at low load, the green lines are actually giving higher efficiency at higher loads where these heavy-duty vehicles may well be operating. So that means that for some applications like heavy-duty trucks or off-highway machines, a hydrogen engine may give a better efficiency than a fuel cell. So that gives two benefits, not only improved time to market, but also potentially better efficiency. So this is really the background to the work that the University of Brighton have been doing with Ricardo, looking at understanding the fundamentals of hydrogen engine combustion, and particularly thinking about some of the challenges for those engines, which are, of course, NOx and efficiency to give the best cost of ownership. So we've been looking at two ways of reducing NOx. One is EGR, exhaust gas recirculation, and the other is looking at higher air-fuel ratios. So some details on this slide of our test setup. So it's a single cylinder engine. So it's one cylinder, which is representative of a typical 6-cylinder truck engine. So it's about 2 litres per cylinder. We've modified this engine for hydrogen combustion. So we've changed the diesel bowl to a bowl which is similar to a CNG bowl to give us a lower compression ratio. So we're running at about 12:1 rather than a diesel 16:1. And we also, in this case, this is a direct injection hydrogen engine. So the hydrogen is injected directly into the cylinder. So we've modified the cylinder head to allow us to do that. And we're using an injector that's supplied by Borg-Warner, which we injects the hydrogen at 35 bar. So a little bit more detail on the instrumentation. So the analyzer from Hariba, which is shown on the right-hand side, is based on a mass spectrometer technology, and that allows us to measure hydrogen in the exhaust. Now, hydrogen slip in the exhaust is important for efficiency, because obviously the engine will be less efficient if you have fuel coming out of the cylinder into the exhaust. But also what we've been discovering over the last 6 months is that hydrogen, although it doesn't have a greenhouse gas, a global warming potential itself, it does interact with ozone and methane in the atmosphere to give it an indirect global warming potential of between about 6 and 16. So it is actually important to reduce any hydrogen emissions, both from the engine and also the supply chain. So in terms of instrumentation, we're monitoring pressures and temperatures around the engine. We're also looking carefully at the emissions. So we're measuring the NOx in the exhaust. We're also looking at oxygen in the intake and the exhaust, because we're using that to calculate the EGR rate. So if we look at the EGR system, we're using cooled EGR. Now, a lot of the EGR benefits are gained from the change in specific heat capacity of the recirculated exhaust gas. So in this case, with hydrogen, where a lot of your exhaust is water, you want to keep the water vapor within the exhaust that you recirculate. So although we're cooling the EGR, we're maintaining the temperature of above about 70 degrees C, so we can keep that water in the exhaust. So as is typical for a single cylinder engine, we're controlling the airflow rate, not with a boosting system, but with a compressor and critical flow nozzles. And then the fuel rate is controlled using the injector opening time. So we can adjust that to give us the power output that we want. So for each test condition, then we're adjusting our spark timing to give the center of combustion at around 8 degrees, top dead center, and then adjusting our fuel and airflow rates to give the required BMEP and AFR. So the test work that we're completing is looking very much at the effect of EGR and changing in air-fuel ratio, lambda, to control NOx. The test work that we've done is across the speed and load range, but I'm just going to present a couple of speeds in a low to medium load today. So looking at first the combustion properties, so particularly looking at duration and stability, so understanding the range of EGR and fuel flow rates that give stable combustion, and also the effect on duration. You'll see that as you increase the amount of air in the combustion, so lambda is increasing, the combustion duration goes up. And also, as you increase the EGR rate, the duration also goes up. You'll also see that there are some changes at lambda 2. So this is where we were having issues with knocking and combustion. So we needed to retard the timing to give us more stable combustion. So that has an impact on combustion duration. And you can see that in the combustion stability plot in that for lambda 2, so the orange graph, you'll see that the LMV of combustion is relatively lower at low EGR rates. Then you'll see at higher EGR rates, so above about 30%, the combustion stability falls off there too. So you have a stable zone of combustion between about 10 and 30% of EGR. So looking in more detail at what happens if your combustion stability isn't good. So this is an example of an adverse combustion condition that we observed, just to show the kind of conditions that might happen if you don't control combustion properly. So this actually is a very rich air-fuel ratio. So this is nearly at lambda 1. And so what we're showing here is intake and exhaust pressure, so we can see how the combustion is affecting them. So intake pressure is the blue line and exhaust is the red. The black peaks then are the cylinder pressure. So you'll see that the first 2 cycles are normal firing cycles. We can see the combustion going on normally. Then the third cycle, then we have a pressure increase in the intake, which is showing that we have some backfire going on. So we don't have our normal cylinder pressure rise. Following that, we have a misfire cycle. So we don't get combustion as we would expect. And then after that, we have pre-ignition cycles. In other words, we have abnormal combustion in the cylinder, which is giving us much higher rate of pressure rise than we would expect. So you can see that from one backfire cycle, the combustion then doesn't recover to a stable pattern. So it's very important to control that properly, which means that as these engines come closer to market, things like closed loop combustion control are going to be very important. However, back on our more stable results out at Lambda 2 and 3, what the good news is for this technology is that what we found is that you can get very low NOx emissions. So this is without after treatment. So this is engine out NOx, looking at ppm. And you'll see that as you, even at no EGR, as you increase the air fuel ratio, so as you increase to Lambda 3, your NOx emissions fall from some thousand of ppm. This is an unoptimized engine, so you might expect to get very high NOx emissions to really lower. And then as you increase the EGR rate, you can get NOx levels below 10 ppm, so really very low. And it's a similar picture across the two speeds that we're showing here at this medium load. So then if we look at hydrogen slip from the exhaust, so what's happening in terms of how complete the combustion is within the combustion chamber. So this is showing hydrogen emissions as a percentage of the exhaust flow rate for different EGR rates. You'll see that looking at the left-hand plot for 900 RPM, as you increase the air-fuel ratio, so as the combustion becomes more dilute, your hydrogen emissions grow. And also as you increase the EGR rate, your hydrogen emissions also grow. And what's interesting, if you look at the shape of the curve against EGR, you'll see that particularly for the Lambda 3 curve, that the hydrogen emissions increase gradually, but then once you get to 30% EGR, they start to increase really steeply. And it's the same picture for the higher speed here. What's interesting to note is that you get higher hydrogen emissions at lower engine speeds. Now, we're investigating this, but we think this is because you get relatively more cooling at a lower engine speed because it's a longer duration, so more coolant has circulated within the head, because when we measure cylinder head temperatures, we find that they are slightly lower at 900 RPM, which makes us think that there's more of a quenching effect on the combustion, so you get higher hydrogen emissions for lower engine speed. So then if we come back to the question we were fundamentally trying to answer, which is then, is there a trade-off between reducing NOx emissions and hydrogen slip? I've plotted here a graph showing changing NOx emissions and hydrogen emissions for 900 RPM and 400 RPM, 1400 RPM, to try and show where that trade-off is. And you'll see if you look at the hydrogen emissions, you see they rise steadily to about 30% EGR, and then they rise very quickly for both 900 and 1400 RPM. And the NOx emissions are falling quickly to a relatively low level between 20 and 30% EGR rate. So it seems that there's a more favourable operating range between 20 to 30% EGR, where you can get relatively low lambda and also before your hydrogen slip starts to increase rapidly. So to summarise, hydrogen engines could give a really good way of decarbonising high power applications quickly, so within the next 5 years. Care is needed with this combustion to avoid any kind of adverse combustion phenomena. But the good news here is that you can get very low NOx emissions, so you can meet requirements for good air quality emissions, and that you can find an area where you can trade off EGR to give you a trade-off between low NOx emissions and hydrogen slip to give you a favourable operating range. So thank you very much for listening, and I look forward to your questions.
Thank you very much, Penny. Very interesting presentation. Our next presentation is by Dr. Alessandro Giampieri. He's a research associate working in the Durham Energy Institute. He currently works on research in low-grade heat recovery, thermochemical energy storage and transport, and liquid desiccant technology. His current projects are industrial heat recovery for heating and cooling with liquid desiccant technology in the automotive sector, and the decarbonisation of low-temperature process heat in industry. So over to you, Alessandro.
Thanks, Tony. Okay, hello everyone. My name is Alessandro Giampieri from Durham University, and today I'm going to talk about the work that I produced in collaboration with Dr. Jenny Chin and Professor Tony Roskilly about comparing the transport of hydrogen and hydrogen carriers from offshore wind farms using pipeline and tankers. I'm going to first describe the feasibility, the potential of producing compressed hydrogen in combination with offshore wind farms. This could help to limit the problem of curtailment of the offshore wind electricity. Then I'm going to compare offshore and onshore hydrogen production strategies together with alternative hydrogen storage strategies such as liquefaction of hydrogen or the use of hydrogen carriers such as ammonia or methyl cyclohexane. Then I'm going to talk about the choice for transport, either using pipelines or tankers. So from the figure, we can see here that in the period between 2011 and 2020, there has been a significant increase in the electricity generated by offshore and onshore wind farms in the UK. But we can see also that this went along an increase of the electricity that was curtailed by UK wind farms. As we know, there is a long-term objective of 50 gigawatt of installed offshore wind capacity by 2030 in the UK. And without significant grid improvement, this will result in an increment of the electricity that is curtailed. Therefore, hydrogen production can be a feasible strategy to utilize the offshore wind electricity that would otherwise be curtailed. In our research, we want to answer the research question: if we want to implement hybrid production of electricity and hydrogen or hydrogen carriers, which pathway would be more strategically viable and cost-effective? Here in this slide, there is the methodology that we used for the study, which was based on data gathering from the literature about energy consumption, capex, lifetime losses, and so on, of the different components that are used. And then we developed a pessimistic, average, and optimistic case for projects starting in the year 2025, 2030, and 2050. Then we defined a case study for which we evaluated 7 different scenarios for hydrogen production and transport. We then modeled the electricity production and the hydrogen production together with the total cost of this type of project, total cost evaluated by factor or by component. Once the total amount of hydrogen and the total cost were calculated, we used them to calculate the levelized cost of hydrogen. And in addition to that, we evaluated with the sensitivity analysis the effect of the storage period and the power output and distance to shore of the offshore wind farm on the levelized cost of hydrogen. Here we can see the 7 scenarios that we are going to evaluate, which mainly are based on compressed hydrogen produced either onshore or offshore, liquefied hydrogen produced offshore and transported to the shore by hydrogen tanker, and ammonia or methyl cyclohexane produced offshore and transported to shore using either a tanker or a pipeline. That's our reference case study that we considered, which is the offshore wind farm Hornsea 2, which became fully operational from the 31st of August 2022. The offshore wind farm is located off the coast of North Yorkshire at a distance to shore of 89 kilometers, and it utilizes Siemens Gamesa 8 megawatt wind turbines. So we wanted to model the electricity production to calculate what's the potential hydrogen production from the offshore wind farm. To do that, we first collected data for the wind speed at the location, and then we combined the data for the wind speed together with the power curve of a Siemens Gamesa 8 megawatt wind turbine. Then we used the wind speed and the power curve to calculate what's the potential electricity produced by the offshore wind farm. Once this was calculated, we used the electricity produced to estimate what could be the hydrogen produced by the offshore wind farm using this formula. What we can see here, what will be different for the different scenarios is the energy consumption of the auxiliary components. For example, when we have liquefied hydrogen, there will be the energy consumption of the liquefaction unit, or when we produce ammonia, there will be the energy consumption of the air separation unit, the Haber-Bosch unit, and so on. So we move further to study the first case, the reference case, which is the production of compressed hydrogen offshore, which is then transported to the shore using a pipeline. Here we can see in the figure all the components that were included in the model. And based on that, we could calculate the total cost of the system and share the contribution of the cost of a single component to the total cost when a very different proportion of the electricity generated by the offshore wind farm is utilized for the production of hydrogen. What we can see from the figure of the total cost is that the cost of the electricity input is the major factor cost of this type of projects. This is particularly due to the fact that electrolyzers are the most expensive component. As we can see, other components such as desalination unit, pipelines, compressors, and so on, they do not affect particularly the total cost, while we can see that the cost of storage is quite important. It's important to mention here that we consider for the calculation a storage period of 14 days. And as I will mention in another slide, when we change the storage period, this will change the feasibility, the choice of the best performing storage strategy. We can also see here that for projects starting in 2030 and 2050, there is a significant reduction in the total cost. This will be due to the reduction in capex of the particular of the electrolyzer due to mass production of them, and also to an increase in electrical efficiency. Based on the total cost and the hydrogen production, we can then estimate what could be the levelized cost of hydrogen. Here we have the formula that we used for the calculation, and we also considered an interest rate of 7% and the lifetime of the project of 40 years. As we can see, for projects starting in 2025, we have a range between the pessimistic and the optimistic value, and we see that a value levelized cost of hydrogen ranging between 5 and 8 pounds can be observed for projects starting in 2025. This is significantly reduced for projects starting in 2030 up to 2050, where the price can be cost competitive with that of gray or blue hydrogen. Moving further, we have scenario 1, which is similar to the reference case, but we have here the electricity that is transmitted to the shore using a high voltage direct current transmission line. Then at the shore, this electricity is used for hydrogen production. Here, compared to the previous case, we won't need a desalination unit, but rather we can use fresh water for the electrolysis process. Here we have the figure for the total cost. As well, we can see a significant reduction in the total cost. However, the total cost will be higher than the scenario in the reference case scenario. And here we can see the contribution of the single components to the total cost. And here the cost will be, the higher cost will be due to the cost of the high voltage direct current transmission line in particular. We can therefore calculate the levelized cost of hydrogen for hydrogen produced onshore. The levelized cost of hydrogen will be slightly higher than the reference case, but we are still getting a value for projects starting in 2050, which is about 2.5, 2.6 pounds per kilogram. Then we wanted to evaluate not just compressed hydrogen, but alternative strategy for hydrogen transport and storage, or the use of hydrogen carriers. We can see here this figure produced with data collected from the literature to compare different strategies for hydrogen transport and storage or hydrogen carriers from an energy demand point of view. And we will particularly focus in this study on liquid hydrogen, ammonia, and methyl cyclohexane toluene. So for scenario 2, which be the production of liquefied hydrogen, which is then transported to the shore using a tanker. Therefore, we will have a liquefaction unit, which will be responsible for important cost and important energy consumption. Then the liquefied hydrogen will be either stored or transported to the shore, and then the tanker would be unloaded and sent back to the offshore platform to load again the liquefied hydrogen. Here we can see the total cost. Compared to the previous figures, here we'll have also a cost for the fuel used to transport the tanker from the offshore platform to the shore. However, for the reference case study, which is located at a distance of 89 kilometers, the cost of the fuel will be not significant. We can also see the contribution of the cost of the single component to the total cost. Here, the cost of the liquefaction unit will be important. However, we can also observe an important reduction in the cost of storage compared to the case for compressed hydrogen. This is because of the significantly lower capex of liquid hydrogen storage compared to compressed hydrogen. That's the figure for the levelized cost of hydrogen, which is somewhat different from what we observed for the compressed hydrogen produced either offshore and onshore. What we can see for projects starting in 2025, that there is a high price and also a much larger uncertainty on the price of levelized cost of hydrogen using liquefied hydrogen. This will be related in particular to the liquid hydrogen yield, the capacity of producing a significant amount of liquid hydrogen from the input hydrogen that is produced by the electrolyzer. And we can see that for projects starting in 2030 and 2050 that the cost and the uncertainty will be decreased, and in particular in 2050 optimistic scenarios which consider zero boil-off storage of liquid hydrogen would make the technology more feasible, more cost-effective, and we can see actually that for projects starting in 2050 there is the potential of reaching a levelized cost of hydrogen which is the same or actually lower than the cost of compressed hydrogen. Moving further, scenario 3 will evaluate the production of ammonia, which is produced using nitrogen is first produced using a air separation unit, which is then mixed with hydrogen to produce ammonia, which is either stored or loaded in a tanker, which is then sent to the shore where it's reconverted to produce hydrogen. We can see here the figure for the total cost and the contribution of the cost of the single components to the total cost. What we can see here, again, that the cost for fuel would be not significant, but here, compared to the previous cases, we will have a quite important cost for the heating, which is required for the ammonia cracking process on shore. We can see here the energy consumption, which is important for ammonia conversion, ammonia synthesis, and ammonia reconversion, while the cost of the storage, the contribution of the cost of the storage tank and of the tanker on the total cost will be not particularly significant. Here there is the figure for the levelized cost of hydrogen, which we can see that for projects starting in 2025, this will show a higher value of levelized cost of hydrogen, which ranges between 7 and 12 pounds per kilogram. This cost could be further reduced for projects starting in 2030. And again, in 2050, the price could be cost competitive or actually lower than that of projects using compressed hydrogen. Moving further, we have scenario 4, which is similar to scenario 3, but it will rather utilize a pipeline for the transport of ammonia from the offshore wind farm to the shore. Here we have the figure for total cost and the contribution of the cost of the single component to the total cost, which are somewhat similar to the cost of scenario 3. The difference here will be that we'll get a slightly lower cost compared to scenario 3. Therefore, we can also see from the levelized cost of hydrogen that is slightly lower. For the reference case study and the distance to its distance to shore of 89 kilometers, for the production ammonia seems more reasonable, more cost effective to utilize a pipeline rather than the transport by tanker. Going further, we have scenario 5, which is about the production of methyl cyclohexane produced offshore and transported to the shore using a tanker. Here we will need for the process toluene. So we mix toluene with hydrogen to produce methyl cyclohexane that is either stored or sent back to the shore using the tanker, and then is reconverted to produce hydrogen. What will be the difference here compared to the transport by tanker using liquefied hydrogen or ammonia is that while in the other cases the ship, the tanker, after go to the shore will go back to the offshore platform unloaded. In this case, we'll have to load it again with toluene, which is required on the offshore platform to form methyl cyclohexane. We can see here the figure for the total cost and the contribution of the cost of the single component to the total cost. Compared to the previous process for ammonia, we can see here that in particular the the methyl cyclohexane reconversion process will be, the energy consumption and cost will be more significant. Here we can see a figure for the total, the levelized cost of hydrogen. We get cost that is slightly higher than the cost of compressed hydrogen for projects starting in 2025, but the cost will be significantly decreased again in 2030 and 2050, where in 2050 could be cost competitive or cheaper than production of compressed hydrogen. Moving further, we have scenario 6, which is similar to scenario 5, but it rather utilizes a pipeline instead of the tanker for the transmission, for the transport of methyl cyclohexane to the shore. The difference here for scenario 6 and the use of methyl cyclohexane by pipeline compared to the use of compressed hydrogen or transported by pipeline or ammonia transported by pipeline is the fact that because we need toluene to be sent back to the offshore platform, we will need a two-way pipeline for this type of process. Here again, we can see the total cost, this important cost for heating, and also the contribution of the total the cost of the single component to the total cost. And we can see that the cost of the pipeline will be large, quite large, and this will result in the fact that for methyl cyclohexane, we can get a slightly lower levelized cost of hydrogen with the tanker rather than with the pipeline, in opposite to what we observed for ammonia. And therefore, it seems more reasonable if a project using methyl cyclohexane is realized to use a tanker rather than a pipeline, because the cost of the two-way pipeline will be larger. Going further, we discussed before the effect of the storage period on the levelized cost of hydrogen. We considered in all the figures that I've shown before for the 7 scenarios, a storage period of 14 days. What we can see here from this figure is that if we reduce the storage period up to 1 day or 7 days, this will make the scenario of producing compressed hydrogen offshore more cost effective. On the contrary, for projects, in particular for projects starting by 2030 or even better by 2050 and the long storage period, alternative strategies for hydrogen storage and transport, such as liquefied hydrogen, could be cheaper, more cost competitive than compressed hydrogen. Then we evaluated the effect of the power output of the offshore wind farm and this distance to the shore on the levelized cost of hydrogen. To develop this calculation, we used the same wind data that were collected for the offshore wind farm, and we created 5 hypothetical scenarios for the offshore wind farms with different power output and different distance to the shore. This calculation was realized to show what? That the most important thing is that the choice of the best performing strategy for storage and transport is for this type of processes is affected by the power output of the offshore wind farm, and in particular by its distance to the shore. What we observe for the project starting in 2025 is that compressed hydrogen produced offshore is the best option. However, this is true only for a relatively short distance, and we consider 1,000 kilometers as this distance. But as we increase the distance of the offshore wind farm to the shore, this will make more and more less cost effective the feasibility of producing compressed hydrogen and transporting it by a pipeline. And in this case, alternative strategies for hydrogen storage and transport should be considered. And in particular, for projects starting in 2030, even more by 2050, alternative strategies such as liquefied hydrogen or production of methyl cyclohexane are promising and seems to be more cost effective than using compressed hydrogen. This work is not completed yet because we consider at the moment a fixed price for the electricity produced by offshore wind farm based on the IRENA report. What we want to do now is to include in the model a flexible model for electricity price, which would allow the offshore wind to hydrogen project to either sell the offshore wind electricity to the grid when the electricity price is high, or on the contrary, use the offshore wind electricity for the production of hydrogen or hydrogen carriers when the electricity price is low. This has the potential to increase the cost effectiveness of offshore wind to hydrogen projects, and to evaluate the economic feasibility, the economic benefit of this type of process. We will implement, in addition to the analysis of the levelized cost of hydrogen and net present value analysis. And this will help also to identify what could be the optimal proportion of offshore wind electricity that should be used to produce, routed for the production of hydrogen or hydrogen carriers. And in addition to that, we want to also evaluate alternative strategies for hydrogen transport and storage, or alternative hydrogen carriers. We want to include it in the model. And another point that could be included in the model is that at the moment we consider the production of the transport of hydrogen or hydrogen carriers up to the shore. We want also to include what could be the effect of transporting it, distributing it to a refueling station. In this slide, there is a summary of the conclusion of the study. Which the most important is that significant reduction in capex and increase in energy performance are expected from projects starting in 2030 and 2050, which would make the levelized cost of hydrogen significantly better for projects starting in this period of time. Also, we evaluated that the cost of electricity input is the major factor of cost for this type of project. And this is mostly due to the electrolyzers, which are the most expensive components for all the evaluated scenarios. We also identified that for projects starting in 2025, compressed hydrogen produced offshore could be the most feasible strategy. And also we observed that the levelized cost of hydrogen may reach values of about £2 per kilogram or lower for projects starting in 2050, which would be cost competitive or cheaper than the cost of blue or gray hydrogen. We have also identified how the storage period affects the choice of the best performing strategy for the transport of hydrogen or hydrogen carriers, and how the long-term storage, such as 14 or 31 days, will reduce the cost of effectiveness of producing and selling compressed hydrogen. We have also evaluated the fact that the distance to the shore decide if it's more cost effective to use pipelines or tankers for the transport of hydrogen or hydrogen carriers. And we identified 1,000 kilometers as the threshold value, where after that, for longer distances, pipelines would not make sense from an economic point of view, and tankers are therefore required for the international or intercontinental transport of hydrogen and hydrogen carriers. And thanks for your attention.
Thank you, Alessandro. It's very good presentation of the research work that's been carried out. I now would like to introduce our next speaker, Dr. Colleen Jackson. Colleen is currently a postdoctoral fellow on the Further Fuel Cell project funded by the EU Fuel Cell and Hydrogen Joint Undertaking, looking at a better understanding of proton and mass transport through catalysis layers in hydrogen fuel cells. Prior to this, Colleen worked on the Memphis project, also funded by the same EU funding, investigating electrocatalysis for hydrogen electrochemical compression. Colleen obtained her PhD as part of a Newton Advanced Fellowship Partnership between the University of Cape Town and the University of Southampton. Over to you, Colleen.
Thank you very much. So thank you for the introduction. So this project is on assessing the electrochemical hydrogen pump for deblending and purification of hydrogen from repurposed natural gas grids for use in hydrogen. And as mentioned, this project is taking place at Imperial College London with our collaborators at the National Physical Laboratory. So some context behind this project is that about 22% of the UK's total greenhouse gas emissions comes from home heating. And so if the UK is to meet net zero targets by 2050, something needs to happen with the natural gas grid. And there are a few strategies for this. The first being completely getting rid of the natural gas grid so that you don't have the CO2 emissions from the grid, and home heating is done by heat pumps. The second strategy is replacing the gas in the natural gas grid with hydrogen. And our project looks at this scenario where if the natural gas grid is replaced with hydrogen, can we use that hydrogen in refueling stations to refuel fuel cell cars and buses? The reason we want to use an electrochemical hydrogen pump, or an EHP, is because you can purify and compress hydrogen in a single unit. The EHP works by feeding impure hydrogen to the anode, where the hydrogen oxidation reaction takes place. The protons then travel through the polymer electrolyte membrane and are reduced at the cathode to form pure hydrogen on the cathode. There is also a pressure differential between the cathode and the anode, which is derived by the energy put into the system, which tracks the Nernst equation. The purification of the hydrogen comes from this membrane, which predominantly only lets protons through the membrane so that you produce pure compressed hydrogen on the cathode. Another benefit of the EHP is that it's easily scalable at different sources and is cost effective. The energy requirement for an EHP is also advantageous when you compare it to traditionally mechanical compressors. Since the EHP is an isothermal process, in general, the EHP uses about 50% of the energy requirement of a mechanical compressor. And as I mentioned before, this energy requirement tracks the Nernst equation. So one of the challenges in this project is that the purity that you need for fuel cells and refueling stations is very, very high, and is typically dictated by this ISO standard, stating that the purity of the hydrogen needs to have less than 0.2 ppm of carbon monoxide, less than 2 ppm carbon dioxide, less than 100 ppm of methane, and less than 2 ppm of all other total hydrocarbons, with the exception of methane. And then finally, less than 4 ppb of sulfur compounds. Whereas the natural gas grid, the gas in the natural gas grid has a number of different compounds in it, listed here in the orange box, as well as an odorant in the form of sulfide, so that you can smell if there's a leak. So in order to meet these ISO standard targets, the methane in the natural gas grid needs to be purified by 10,000 times. These other compounds also need to be, in the orange box, need to be purified by 10,000 times, and the odorants in the form of sulfides need to be reduced by 420 times. So this is a significant challenge. The biggest problems are the carbon dioxide, since when it's in contact with a platinum catalyst, specifically in a fuel cell, is it reacts via the reverse water gas shift reaction to produce carbon monoxide, which is even more poisoning to the platinum catalyst used in a fuel cell. The same can be said for sulfides, which is also poisoning of the platinum catalyst. So as I mentioned before, the platinum catalyst, which you'd find in an EHP and a fuel cell, does the hydrogen oxidation reaction to produce protons and electrons. If it's in the presence of carbon monoxide, this strongly binds to the platinum surface, which then reduces the number of sites which can undergo the hydrogen, which can catalyze the hydrogen oxidation reaction, and reduces the performance of the system. This is especially true for sulfide compounds, and that's why the ISO standard is so low at below 4 ppb of these sulfides, because sulfur is even more strongly bonding to platinum. And in some cases, one sulfide, a molecule can take up to 8 platinum atoms. So it has a significant poisoning effect on these catalysts. And these are the catalysts we use both in EHPs and in fuel cells. One strategy for dealing with this poisoning in a fuel cell is called an oxygen bleed, where you add a very, very small amount of oxygen to your hydrogen stream. And this is around 1% oxygen in hydrogen, which is well below the flammability limit of 4% oxygen in hydrogen. And this very small amount of oxygen allows for the platinum to help oxidize off the carbon monoxide to carbon dioxide, and then So that frees up the platinum catalyst to then catalyze the hydrogen oxidation reaction. So this is typically used in fuel cells, and there are some similarities between an EHP and a fuel cell and some differences. So if we look at the fuel cell here, like the EHP, we have the hydrogen oxidation reaction on the anode. We have protons transferring through this polymer electrolyte membrane, and then we have the oxygen reduction reaction on the cathodes. We have oxygen, either pure oxygen or in the form of air on the cathode. So in a fuel cell, if we have small amounts of carbon monoxide at the anode, this, as I mentioned before, will strongly bind to the platinum catalyst and poison this catalyst. However, in the case of a fuel cell, you have oxygen which may cross over from the cathode to the anode and assist in oxidizing off the CO from the platinum surface. If you have CO2 in the anode, this may cross over from the anode to the cathode and undergo the reverse water gas shift reaction to produce carbon monoxide, which will then poison the platinum catalyst at the cathode. However, again, you have oxygen on the cathode, which could then assist with oxidizing off this carbon monoxide from the catalyst surface. So a key difference to the EHP is that you don't have oxygen on the cathode to assist with any oxidizing. So an EHP is going to be far more sensitive to inclusions of CO or CO2, but you're also not limited by overpotential at the anode like you are in the fuel cell. And this phenomenon has been scarcely studied, but you can predict a sacrifice in performance if you are including these types of poisons in an EHP, just as you would in a fuel cell. So we did work on a similar project before called the Memphis project, and this looked at purifying hydrogen using reformate gas. And reformate gas has a similar similar compounds in that there is methane, CO2, carbon monoxide, and hydrogen sulfide in the feed. And we found that if we didn't have a bleed, the cell would die in about an hour and would not be able to operate with reformate gas to the anode. However, if you include an oxygen bleed, you can operate the EHP with about 60% of its initial current density with pure hydrogen. We also found that if we added a very, very small amount of ozone, so 0.05% of ozone, which is a very strong oxidizing agent, you can then further increase the performance of your EHP to about 75% of your initial current density with pure hydrogen after about 7 hours. We then looked at different concentrations of H2S. So we looked at 100 ppb of H2S to the EHP. And again, we found with this very small amount of oxygen and ozone bleed, we can operate at about 76% of our initial current density with pure hydrogen. So moving on to the scope of the study for the Network H2 project is we wanted to look at how the EHP might operate with natural gas. And so work package 1 consists of looking at different compositions of pure methane in hydrogen. And then moving to work package 2, we now looked at the natural gas with all of its impurities, including an odorant, on how the EHP could operate. And then work package 3, we included this the small bleed with oxygen and ozone to see how we might mitigate this poisoning due to the impurities in the natural gas. So first, looking at work package 1, we looked at the effect of different operating conditions, so different concentrations of methane, different stoichiometries to the anode, and different current densities. So what we found was that there was no effect on inlet stoichiometry on the gas purity. However, the current density that we operated significantly affected the purity of the methane. So in general, we could purify the methane by 4,000 to 16,000 times in the EHP via this membrane. And this was strongly correlated to the current density. What we found was that the methane that crossed from the anode to the cathode was independent of the current density. So the higher your current density, the more hydrogen you evolve on the cathode, which dilutes the methane that you have that has crossed over the membrane. So in order to reach methane concentrations of less than 100 ppm, you need to operate with current densities of about 0.3 amps per square centimeter or higher, so that you evolve enough hydrogen to dilute the methane that's crossed over. A surprising element or molecule that we detected in the product stream is CO2. Even though we weren't including CO2 in the anode, we found CO2 in the product stream, about 0.5 ppm of CO2 in the product stream in work package 1. So this could come from two different sources. The first could be that methane is reacting by the methane oxidation reaction at the anode to produce CO and CO2. However, we also saw CO2 in the product stream when we didn't have methane at the anode and we were only operating with hydrogen. So then we decided that it was likely that the CO2 was coming in with the water supply, a small amount of CO2 being dissolved in the water supply, which we're using to humidify the membrane, but still well below the ISO standard of 2 ppm. If we move on to the energy requirement for this hydrogen separation in an EHP, we found that compared to the pressure swing adsorption, which is the industrial standard for hydrogen purification, that some operating conditions for the EHP had lower energy consumptions than this pressure swing adsorption. However, this pressure swing adsorption value is an ideal for a pressure swing adsorber of around 12.5 kilowatt hours per kg, which generally operates with steam methane reforming with about 80% hydrogen and less than 50 ppb of H2S. If you were to try and operate in a pressure swing adsorber with a natural gas, you would have much higher energy consumptions since you have this high sulfide concentration, which would also poison the adsorbers used in pressure swing adsorption, and you have a lower hydrogen content, so you'd have to increase the energy consumption of your pressure swing adsorber. So in general, we'd expect this PSA using natural gas to be much higher, and we see that the EHP is competitive in terms of energy requirements. However, if we switch from pure methane to the natural gas, which has these other compounds which would poison the catalysts, we see that we can't operate the EHP with this natural gas without a bleed, as the cell would die in about 2.5 hours with 50% natural gas and in under half an hour with 80% natural gas. But if we include our small amount of oxygen in terms of a bleed and ozone, we see that we can operate for much longer periods of time of around 6 hours if we include the bleed. However, there was some evidence that methane could be reacting with that very small amount of ozone to produce CO and CO2, which then further poisons the catalysts. So it could be that only an oxygen bleed we can only operate with an oxygen bleed rather than an oxygen and an ozone bleed. So looking at the purity under these conditions with the natural gas, with 80% natural gas to the anode, we can purify that to below 100 ppm of methane if we operate at 0.3 amps per square centimeter. At lower current densities, we have much higher concentrations of methane of about 200 ppm. So we need to operate with current densities of 0.3 amps per square centimeter or higher. This is true too for if we have methane or natural gas concentrations of 50%, we need to operate at 0.3 amps per square centimeter. What we also found was, as I mentioned previously, if we're operating with ozone, we did detect a very small amount of carbon monoxide, so in the order of 0.02 to 0.06 ppm of CO, which confirms that we could be reacting methane with ozone. A much bigger problem that we didn't anticipate at the start of the project is CO2 crossover in the membrane. Since you only have about 0.8% CO2 in the natural gas stream, we didn't predict that it would be a problem purifying that CO2 to below 2 ppm to meet the ISO standards. However, we find that much more CO2 manages to cross the membrane when compared to methane. So if we operate with 80% natural gas at 0.3 amps per square centimeter, we have about 25 ppm of CO2, which crosses the membrane and makes its way into our pure hydrogen stream, which is much higher than the 2 ppm of CO2 that we need. This is also true for 50% natural gas, where we have about 20 ppm of CO2 at 0.3 amps per square centimeter. So CO2, surprisingly, is a large issue, and we need to consider it separately to methane purification. So to conclude, generally the EHP purifies the methane very well by between 4,000 and 16,000 times, depending on the current density, where current densities of about 0.3 amps per square centimeter reach the ISO standard of less than 100 ppm. But we cannot operate the EHP with natural gas without including a bleed. And this purifying of carbon dioxide is a much larger challenge than purifying the methane in the natural gas. So moving forward in this project, we're going to look at lower natural gas concentrations of about 20%, so that we can see where the limit is in the natural gas concentration, so that we can meet the ISO standards on the cathode. So that's it for me. Thank you for your attention.
Thank you very much, Colleen, for a very interesting presentation. So we're going to go on to this afternoon session now, and a keynote presentation by Professor Tim Mays. Tim is Professor of Chemical and Material Engineering and head of the Department of Chemical Engineering at Bath University. He has broad research interests in engineering and energy materials, with a current focus on hydrogen storage media for low carbon road vehicles. He is currently co-director of the EPSRC Centre for Doctoral Training in Sustainable Chemical Technologies and the EPSRC Supergen Hydrogen and Fuel Cell Hub, and director of the university's Institute for Sustainable Energy and the Environment. And if that's not enough, he also leads the EPSRC's research initiative on hydrogen and hydrogen-based low carbon fuels. Tim, over to you.
Well, good afternoon, everyone, and thank you very much to the conference organisers for inviting me to speak today. We've heard some very interesting and important technical talks so far at this conference. I'm going to give a much more general talk about a project that we're running at the moment that will hopefully be of interest to many of you. So I do apologise for not going into too many technical details, although I'm very happy to answer any questions if anyone has any. So what I'm going to do is to summarise the coordinator project that we're running at the moment, funded by EPSRC. And the aim of this coordinator project is actually to build a hub for research challenges in hydrogen and alternative liquid fuels. And hopefully you'll learn a little bit more about how that will work as I move through the talk. I think it's important to I always want to remind myself why I'm doing my work, why I'm doing the work that we do. So there's an urgent need to reduce carbon emissions from declining fossil fuels. This is to mitigate the horrific impacts of this on planetary boundaries, in particular climate change. The obvious solution that we should all be investing in is renewable energy. But to manage intermittency and distributed production, energy storage is going to be essential as part of the managing our renewable energy resource in the UK. And options include especially hydrogen and its carriers. And hydrogen is a wonderful and flexible energy carrier for whether it's power, heat or transport. And obviously transport is the main interest today, but it has a broader church of interest in our energy system, and also in energy decarbonisation, but I won't be able to spend much more time on that today. I think, again, it's important to remind, I always look at this and sort of throw my hands up in dismay, but since the pre-industrial times, atmospheric CO2, as a result mainly of fossil fuel combustion, has gone up by 50%. It's remarkable, really, in recent history. And the reason I put 2003 on that's when I started to work in hydrogen. And even since then, it's gone up by 11%. So it's something that's happening today. It's not something that's going to happen or did happen. It's happening today, and I think that this is always useful to remind ourselves about that fact. And another incredibly useful way of articulating the impacts of climate change is this Ed Hawkins climate stripes. This is over sort of 70 odd years, more than that, 120 years of climate change or temperature change data. A white stripe means the average over this period. So blue is cooler, red is warmer, and you don't really need to even say much about the fact that over the recent history, certainly since the 80s and 90s, we're seeing every year as the warmest year yet. And of course, the consequences of this are climate change, not the weather. It's climate change. And the left images sort of illustrate what's happened recently, the terrible floods in Pakistan, which are almost certainly a result of a change in the climate, not just a bad day for the weather. And perhaps less important, but probably still newsworthy, is the fact that we had these remarkable high temperatures in the UK recently in our summer, 40 degrees, that's 104 degrees Fahrenheit in old money. And these are not weather effects, they're climate change effects. And I think that the jury is not out on that. The jury has submitted their conclusions to the judge, and we really need to do something. And of course, planetary boundaries is another way of articulating the various aspects of our world that we need to be careful with. Climate change being one of them, but of course there are lots of other freshwater use, aerosol loading, ocean acidification. And if I may say so, I've heard today or recently about removing CO2 from air. I'm not sure that makes sense to me, because if you do that, a lot of the CO2 dissolved in the oceans will just come off again. So I don't know whether that's a viable option, but maybe I'm wrong. But the fact remains is that climate change is one of these planetary boundaries where we need to be very, very careful about how we manage our environment. Now, in the UK, there are lots and lots of policy instruments that are there to help us through this, and particularly the concept of net zero, which came along in 2019 as a result of the amendment to the Climate Change Act, which stated very clearly we go to net zero. And obviously the reference point is irrelevant. It goes to net zero in 2050. And these are four probably the ones that have high in our minds about how the UK intends to manage that. The 10-point plan, which I'll come on to in a minute, the hydrogen strategy, which everyone interested in hydrogen should read. The net zero strategy, which is about how we build back greener, according to the title, but it gives more detail about how the UK could and should develop. And recently, the energy security strategy, clearly prompted by geopolitical uncertainty, especially in Central and Eastern Europe. And I personally think that the reignition of interest in hydrogen came about especially after the net zero statement from the Climate Change Act. Before that, it was seen as useful and interesting, but not necessarily something that we should engage too much with. After that, people probably said to themselves, well, hang on a minute, what on earth are we going to do? And obviously hydrogen has come way back into our thought as an option to help us meet this very significant challenge. And actually, up until now, we've not been doing too badly. We sort of more or less halved our emissions since 1990, but the problem is for going forward that it's going to be a tougher challenge going to net zero than it was getting to the point we are now, which is about halfway through this period. And I think that while these carbon budgets are very useful, the dotted line on here suggests what we should be doing to achieve net zero, and I'm not sure that we're necessarily on the right journey to achieve that with current policies, and especially those that have come about recently with the change of Prime Minister, but we'll see. Now, the 10-point plan propagated by the previous Prime Minister identified 10 areas of particular focus and interest to help us achieve net zero, and you can see them here. And I put a tick next to every single one of them, because I think that hydrogen has a role to play in all of them. So this is a point to make, that hydrogen doesn't just, you don't just make the stuff and put it in a fuel cell or a heat engine. It has a role to play in many of these, or in fact all of these at various levels. But the obvious high profile part of this is point 2, which is the delivering of driving growth of low carbon hydrogen. And today, for this conference, the link with transport for zero emission vehicles, point 4, green public transport, point 5. And we already heard today about hydrogen fueled aircraft. So the Jet Zero initiative and green ships, marine is another aspect of transport. And so it's land, sea and air transport where hydrogen could play an important and should play an important role as we defossilize, once we move away from oil, coal and gas. Incidentally, the ticks and the boxes are not listed in the plan. I put them in. EPSRC, UKRI, considered what the options were in moving forward after the end of the sort of supergen programs, and the hydrogen supergen program will finish at the end of this calendar year, and came forward with a proposal to identify so-called hydrogen research coordinators. The idea being that these coordinators will then build national programs, not Supergen 2 or Son of Supergen, but a rather different approach to a national program. And I would encourage everyone who's interested in how these things work to have a look at the call. It's still there. Obviously, it's not live anymore, but it's still there. And it gives a very clear idea of the ambition behind the call and what the EPSRC in particular, they're the main funders of this program, will want to achieve. It's a very significant and ambitious program. And after the appropriate assessment and interviews and so on, we were lucky to be able to be awarded that. If you want to have a look at the details, that's on the EPSRC website on grants on the web. And initially the budget was for 6 months from the 1st of April. So we're about a week or two away from the official end for this phase 1, but I'll come back to that in a minute. In fact, there are 2 projects, coordinator projects, one run by my colleague Sarah Walker at the Newcastle University called HIACT. And I would encourage you to have a look at the website that they've set up and also the grant award details. And this is about systems integration. How can hydrogen be integrated into systems? And you can see at the top right the areas that they're being encouraged to cover. Now on the left, we've called our research coordinator project UK HiRes, or just HiRes for short. And this is low TRL research 1 to 3, all mostly in the engineering and physical sciences space, and with identified and clear impacts leading to net zero. So that'll be one of the main criteria for projects to be funded as part of UK HiRes. We aim to be interdisciplinary and cross-cutting, and have significant interaction with industry, co-creation of projects, co-funding, and co-supervision of projects. But right at the start, we were completely agnostic about technologies. We did not come in with any preferred or areas that we wanted to promote or those that we wanted to demote. So there's certainly a focus in the UK initially, but the international development will come along later. Naturally, we're going to be very keen to make sure we have engaged with equality, diversity and inclusion, and also, and importantly, responsible innovation and ethics as part of what we do. And I think we shouldn't also forget that these UKRI or EPSRC funded projects do build sustainable capacity and talent pipelines in our research communities. Now, this is the slide we produced when we were interviewed. One slide at interview. Some of the wording's changed a little bit since that, because, for example, the centre that we originally envisaged is now going to be called a hub. But the process was leading to identification and prioritisation of research challenges within a specified budget, which wasn't given at the time, but we now know is 12.5 million FEC from the 1st of April 2023 or soon after that. And the process we're using to identify and prioritise research challenges is so-called theory of change. Some of you may know about this. It's a way of identifying what are the drivers for the work, what are the barriers for this work to be done, and what are the main challenges involved. How does that lead to what opportunities for research, and what outputs will these deliver? Do these outputs lead to change? Will they lead to, for example, cost reduction, emissions reduction? And obviously this eventually leads to the impact. Do these research challenges, if successful, lead to important differences? And obviously the main objective is to lead to net zero and all the strategic work around that. In order to run a project of this side, I've mentioned at the front of the talk, I should have mentioned my co-investigators. I'm PI of the project, Rachel Rothman at University of Sheffield and Shan Wen-Tao at the University of Warwick. And the three of us actually work very well together. We're on about, for your interest, we're on about 0.9 FTE between the three of us. So that's the level of activity that we engage in the project. We have a management team here led by Yanka Kalish, who's the project manager at Bath, fantastic project manager, worth the weight in gold. And we have support at each of the partner universities. And the total FTE of this team, again, is about 0.9. We've recently had a new member of the team that's joined last week. And you'll see at the bottom, we've actually engaged with the collective who do facilitation of meetings, very, very good. I would encourage people to look at them as options if they're organising conferences and workshops, and Scriberia, who are delivering visualisation, which can be very helpful in a whole variety of contexts, schools, policy people, the public. And we've also got a researcher team who do a lot of the legwork behind the scenes. These are 1 FTE each. And again, we recruited very carefully to get the right people for this, and the three of them are fantastic, I would say. In addition, we've got a special advisory team of mainly industrial partners, with 7 of them here, and you can see them here. And I would like to highlight in particular ITM Power and Marcus Newborough, who sat on the panel with us when we were interviewed and has been very, very proactive in being involved in our projects. And of course, ITM are a very important company in this space. And my personal thanks to Marcus for his support. Now, the main events we've been doing, and hopefully some of you have been at some of these events, we decided to run them in themes: production, storage, end use, and alternative liquid fuels, which turned out to be mainly ammonia. And we were due to have a meeting last week, which was cancelled by UKRI as a respect to Queen Elizabeth II, and we're looking forward to rearrange that, but I'll come back to that in a minute. Paul Monks, the CSA at Bayes, was very kind enough to help us with our project launch, and he was due to give a talk at the showcase, but of course that'll be for another day. We also have a pretty good website, so please have a look at the website. There's lots of news on there and lots of information about the outputs of the workshops that we've had. So if you want to have a look about what all the detailed discussions were for the workshops, they're on the website. So we had a launch in May, seems a long time ago now. We had a board meeting. Marcus Newborough was there, Roger Wells from Siemens, Stuart Hawksworth from HSE were there, very helpful participants, really very super advisors, helped us a lot on the way. And what we did was we gathered interest in the project, all the areas by theme, and you can see that a lot of people are interested in production, not a surprise. There's not a lot of low carbon hydrogen around, and that's obviously of interest. About equal in storage and end use, and with a still sizable interest in liquid fuels, mainly ammonia. This is just an example of the visualization that we've paid for to help us communicate, whether it's to schools, the public, policymakers. And I rather like the Swiss Army knife model in the middle, Swiss Army knife, hydrogen turning itself to lots of different things. This often is seen as superficial, but actually communication of research and its outcomes and why we're doing it is very, very important. So we had a workshop on production, and of course that is put into sharp focus by the government's increase of its target for hydrogen production, including low carbon hydrogen to 10 gigawatts by 2030, which has to come from water or biomass. It can't come from fossil fuels. I just don't see it. And there's been a lot of discussion at these workshops and separately about the electrolyzers and biomass conversion, and we also need to deliver liquid hydrogen as well as gaseous hydrogen. That has also been the subject of debate today, and it's something that we need to look at very carefully in the future. So production was a very busy workshop, and there were a lot of ideas that came out of that. Storage, and this is my area, my own research area. So on the left, I divide storage into physical and chemical storage. Physical storage is where hydrogen remains as molecular hydrogen, H2, and this is liquid or solid or compressed gas. These are under extreme conditions of temperature or pressure, or containment in porous solids, which may be able to work at higher temperatures and lower pressures than some of these demanding conditions for liquid and high pressure gas. And that little squiggly molecule there is a polymer of intrinsic microporosity, which we think might be able to help us store hydrogen under reasonable conditions at good capacities. We've heard about blending today, is moving it around into the gas grid at whatever level it might be, up to 20% at the moment. And we have geological storage options and specific pipelines, as well as the sort of existing infrastructure. There's also chemical storage, which is where basically hydrogen forms a bond or is an interstitial, and actually you break the hydrogen molecule into either ionic systems or covalent systems or interstitial systems. And there is a lot of work around the patch on hydrides and complex hydrides, which can deliver reasonable capacities. They can be quite heavy and have other issues, but they're very effective in certain conditions. And of course, ammonia, which I'll come on to in a minute. Now, the end use can either be burning it or putting it in through a fuel cell to harvest the energy, or an industrial gas to make green ammonia, for example. And the sectors are power, heat, and obviously transport. And this is the focus of this meeting, but it's one of the main sectors that hydrogen will have this impact. But industrial decarbonisation, it could either be green ammonia, or it could be in foundation industry decarbonisation, steel, glass, ceramics. And I think that's an option for decarbonising industrial clusters, which people are significantly interested in at the moment. And our final workshop was the broad area which has been handed to us by EPSRC is alternative liquid fuels. And we opened the door to any alternative liquid fuels, and not, in other words, hydrogen carriers in another sense. And ammonia emerged as the lead one, partly because there's also an infrastructure with ammonia. People know how to move ammonia around, how to make it. And it's a well-known industrial gas. People know how to work with it, as indeed they do with hydrogen. And of course, there are other alternative liquid fuel or hydrogen carriers, including maybe formic acid is not my lead choice, but there are others, liquid organic hydrogen carriers, toluene, and so on, and SAF as well, which we've heard of today. Now, one of the, I haven't time to go through all the detailed outputs of the workshops, and I'd encourage you to read the reports on the website, which go into much more detail than I have time for today. But emerging themes that have come out very strongly, and you can see some of that in the word cloud on the right, are materials, internal materials for storage, for production, for end use. And I'll give an example, which was relevant to a talk we heard earlier on today. Liquid hydrogen is seen as a fuel for future aircraft. And carbon fiber reinforced epoxy resin might be one of the materials for containment, but no one knows how this material will behave in contact with liquid hydrogen. So there are this is an example challenge, but it's just one of many that need to be resolved in order to accelerate the uptake of these technologies as we move to net zero. Safety came up again and again and again. And we heard again today what we have, if you have a liquid hydrogen production facility, you need to have exclusion areas and bunds and so on to make sure that everyone's safe. Ammonia came out as an attractive option in and of itself as a fuel, or perhaps as a carrier of hydrogen to crack back to hydrogen. Public engagement seen across the patch is important. This hasn't been emphasized enough. Technology change, you have to bring the public along with you to be aware, to understand what this is and to see the benefits. And also we have to be honest to be familiar with a change in behaviour. For example, how we refuel a motor car if hydrogen comes into that sector. And I don't know about anyone on this call, but I suspect that many of us are confused with the landscape of going on in hydrogen. There's so many people interested in doing things and doing them in different ways and in different formats and different partners. And one of the jobs we want to do with the project we have at the moment is to help with coordinating that and act maybe as an information hub to help people navigate through this sort of complex environment. So what are our next steps? Well, we were to have this workshop, but we hope to rearrange that because we have had confirmation of extension of the project until the end of April next year. But we're doing one-to-one interviews with industry and academic partners in the field in hydrogen and alternative liquid fuels to get a different perspective than you can do in a workshop. We are engaging strongly with Sarah Walker and her systems coordinator project. We have a lot of synergy, but we don't have any strict codependency. So we're working together, but we're making sure we add value to what each of us is doing. That seems to be working well. And of course, we're consolidating our analysis and synthesis of all the engagement outcomes from workshops and from the one-to-one meetings, and that's coming along nicely. And also, and which is what I'm working on at the moment, is responding to the hydrogen call for the hubs. And this came out recently, and the deadline is in November. And again, I would strongly encourage colleagues to have a look at what this looks like, because that will frame what the hub will eventually look like and how it will develop, and not just for the 5 years, which we expect the hub to be running for, from 1st of April next year at the earliest, with a budget, as you can see, of 12.5 million FEC to each hub. But we were looking beyond that, and there's also significant expectation of industrial leverage support, 30% initially, and then rising as the project develops. And we're looking forward to that partnering with industry. So this is a helter-skelter talk, and we haven't come to the end of the project yet, but we're coming to a certain closure, and we're looking forward to developing our hub call and responding to that, continuing our engagement with our community, not only in transport, that's a very important sector, but in the others, heat, power, and industrial decarbonisation. And I do appreciate this is not the detailed technical talk that you have been seeing before, but I'm very happy to share my slides with you. It's either through the network or independently, and I'm also very happy to have an email or a contact via the website, which is here. And with that, I'll finish my talk today. Back to you, Tony.
Thanks, Tim. Tim, thanks for letting us know exactly what's happening with the development of the hub, and very, very interesting future and very exciting for the whole community. Let's move on to our next presentation. This is going to be delivered by Aaron Keith. Aaron is a PhD researcher at Queen Mary's University, London, supervised in conjunction with the University of Oslo. His research also collaborates with the Institute of Chemistry and Materials of Paris East. The focus of the work will be to form high-entropy alloys capable of hydrogen storage for future lightweight automotive applications. Over to you, Aaron.
Thank you very much for the introduction. So my name is Aaron Keith, as introduced by Tony there, and I'm very excited to talk to you all today about our perspective on how the lightweighting of metal alloys, interstitial hydrides, could be applicable for onboard hydrogen storage in vehicles. So we've spoken at this conference quite frequently about the utilization of the physical storage methods. So namely that as liquid hydrogen with the problematic low boiling point and high pressures up to 350 to 700 bar of hydrogen. Both of these not terribly logistically viable and do drive up the cost, as we've seen with liquid hydrogen. So for wide-scaled automotive applications, it's perhaps there might be a better method. So how can we go about transitioning away from the physical storage methods? So we have to go back to the drawing board there of how we actually store hydrogen from the ground up. So switching from physical-based methods with these complications, where we have high pressures of gas and low temperatures, or we can have a hybrid system of the two existing simultaneously. And moving into material-based storage overcomes one of the key problems of physical-based storage, which is the volumetric capacity. So you see a volumetric increase in these systems here, these material-based systems, and you can also tailor the storage of hydrogen to be at much lower pressures, so in the tens of bars rather than in the hundreds of bars, and at near ambient temperatures for certain cases. The key issue with that is that there is a massive decrease in the gravimetric capacity. And while all the material-based solutions are very valid for their research and very interesting and have different applications in their own right, our focus has been on interstitial hydrides. So just to familiarize you all with what they are transition rare earth metal hydrides, such as those on screen here, where hydrogen, pure hydrogen, is introduced to the metal alloys and it adsorbs to the surface of the metal, where it splits homolytically into two hydrogen atoms and permeates deeper into the lattice of the metal and occupies what are known as interstitial sites. So that's these red dots in these diagrams up here. And what we've noticed is that the molar uptake as a maximum for these alloys has an HM, so a hydrogen to metal atom ratio of 2. So the theoretical maximum you could achieve if you had a body center cubic alloy, which is this lattice packing arrangement here on the right hand side, would be 6 if all interstitial sites could be occupied simultaneously by hydrogen. And for the FCC hydride, which is this one here, it would be a theoretical maximum of 3. The problems with these traditional alloys is that you use heavy and often rare elements such as palladium or lanthanum. They're very common proponents and very well studied, which are also expensive, which drives up the cost of utilization, especially on wide scales. It makes them very impractical for a large scale deployment. So one potential solution that could address these issues are utilizing high entropy alloys. So high entropy alloys are multi-component alloys with 4 or more elements in usually equimolar proportions, but in a looser sense can be between 5 and 35 atomic percent, which is these alloys here. The overall, so entropy in the name here, doesn't refer to the lattice packing as it adopts standard lattice arrangements such as hexagonal, face center cubic, or body center cubic packing. So it rather refers to the distribution of the elements within the alloys being randomized. So you have a solid solution. And what's been reported is that the maximum hydrogen to metal atom ratio is 2.5, thus pushing us to closer saturating the lattice. And that belongs to this alloy here. So with respect to addressing the issues of the previous alloys, we have the introduction of lighter elements such as titanium, aluminium, manganese, and zirconium, which are quite a bit cheaper in some cases than the other ones as well. And as a comparison, we can use the example of the alloy with the highest uptake, which is this one here, where we have a hydrogen to metal ratio of 2.5 and a gravimetric capacity of 2.7 weight%, relative to lanthanum pentanickel, which is often cited and reported. And we have a significant decrease in our theoretical uptakes, which is a hydrogen to metal ratio of 1.1, and a gravimetric capacity of 1.5. And as I've said previously, the cost does decrease drastically. And given how broad a scale that we can go with, so 4 elements within a ratio of 5 to 35% are quite broad standards for defining these alloys. The guidelines for the storage that we would propose would be to firstly figure out how to maximize molar uptake in the lattices. So we need to know what those driving forces are. And from there, we can maximize the gravimetric uptake via stoichiometric or elemental substitutions, and thereby bring it into this range that's proposed by the US Department of Energy, which is the common standard when targeting hydrogen storage in onboard applications. So what we would suggest as design parameters for these alloys to start with are, firstly, looking at the lattice packing arrangement that's the most favorable. So the first and foremost, the most favorable arrangement is a body center cubic alloy that distorts into an FCC hydride. This is the same case with the previous example here. And many others follow this. This is just a handful of examples, and they kind of max out at a hydrogen to metal ratio of 2 on average, but the highest example being 2.5. However, being a BCC alloy from the start itself does not necessarily guarantee a high uptake, as we can see with this alloy here with a hydrogen to metal ratio of 0.15. So how can we incentivize a higher uptake from the ground up? We need to look at the elements that we're using. So the classification of metals with respect to hydride formation, there's 2. So you have A-type metals, which readily form hydrides, and B-type metals that resist hydride formation. To quantify which is which, you use 2 values, which is the enthalpy of hydride formation and the enthalpy of solution at infinite dilution. Basically, can you form the bond, and can you allow hydrogen to permeate through the lattice with low impediment? So for the alloys, the way that we can assess ab initio whether or not these values will be favorable is from the weighted average based on the stoichiometric proportions of the elements included. So if we increase our proportions of titanium, for example, we'll have a better affinity ratio values, and for iron, the converse. So given that these alloys, the affinity of these alloys is the weighted average of the components, and strongly exothermic values are preferential for this increased uptake, what's been found is that you can improve both of these values by stoichiometric and elemental variation. So we have an example here of the theoretical alloy, which is equimolar for magnesium, aluminium, titanium, manganese, and niobium, which gives us these values here of 32 and 8. And via simply tweaking the stoichiometric proportions of the elements involved to non-equimolar, we can triple the affinity value for the infinite dilution while still increasing the formation value. And this can explain why the previously mentioned alloy, the BCC alloy of magnesium, vanadium, aluminium, chromium, nickel, has a poor uptake, as it comes down to a very poor enthalpy of solution infinite dilution, which resists the permeation of hydrogen throughout the lattice. So just to kind of sum up there, what I've been speaking about is that the affinity values can be a very useful tool in designing these alloys, which offer a higher molar uptake. From there, we can substitute in ab initio different elements that are lighter. So say substituting tantalum for vanadium, as they are isoelectronic, might offer a way to retain that high molar uptake while reducing the gravimetric and increasing the gravimetric capacity. And that moves us in line with the Department of Energy's targets. Another very important parameter that's often cited is the valence electron concentration. So the valence electron concentration is of an element is the number of electrons in the valence band. And for the alloy, similarly to the affinity values, it's the weighted average of the components. as seen here. And what's found for the alloys that have a VEC lower than 6.86, you can incentivize the formation of a BCC alloy, which was the most favorable alloy packing arrangement from previous examples and the most successful examples of alloys. Though it has been recently proposed that if you have a VEC that's greater than 5, so between 5 and 6.86, you'll still get your BCC alloy. However, it does not follow the favorable distortion pathway into the FCC hydride. So keeping the VEC yet lower than 5 is favorable. The valence electron concentration has also been proposed as a means to assess various other parameters like the onset temperature of desorption, though it must be stressed that further study is required to corroborate or deny that. In line with this, the randomness of elemental distribution is one of the key differences between high entropy alloys and their traditional alloys. So if totally random elemental distribution occurs, upon cycling, your phase separation is less likely to occur. So that gives you more reliable and higher storage performances. So there's two methods that we can assess that. So we can use the Hart spheres model proposed by Ye et al. It's based on a Mansouris model from, I believe, the 80s, 70s, 80s. And unfortunately, due to the complications with defining this term here, the entropy, the excess entropy of the system in relation to the entropy of conformation, it is very time consuming and computationally demanding. So another method that can help ease that computational burden is using a bidimensional approach, which is based on the Gibbs free energy of equilibrium, which again refers to, and also refers to the lattice distortion. And again, it is more time sensitive, though you do sacrifice a great deal of precision relative to the phi value. So just to highlight the Gibbs free energy method, this is a plot. So this peach range here is where you are likely to find high entropy and random elemental distribution, though there is a sizable overlap where solid solutions and intermetallics coexist. So if you're within this range of the omega value here on the y-axis, greater than or equal to 1.1, and the distortion less than or equal to 6.6%, you're likely to form a solid solution. However, to really be precise and decide whether or not your composition will form that high entropy random distribution, you might want to corroborate with the assessment of the phi value, which is greater than 20 is going to be a single phase. If between 10 and 20, you'll have multiple phases, maybe some amorphous phases occurring closer to 10, and anything less than 10, you're likely to have an amorphous distribution. So from our perspective, just to tie everything together, high entropy alloys offer an improved hydrogen storage capacity relative to the traditional interstitial hydrides. Their storage capacities can be enhanced by maintaining advantageous affinity values by balancing the two enthalpy values. And that can be further incentivized by varying elemental and stoichiometric compositions. From the most favorable structures, which is a BCC that distorts into an FCC hydride, that can be incentivized to form if the valence electron concentration is kept lower than 5. And random elemental distribution allows for more reliable performances, and that can be assessed one of two ways, unidimensional or bidimensional, with pros and cons for either method. One key sort of finding from the assessment of FCC hydrides is anomalous octahedral site occupation. So an FCC hydride where the hydrogen to metal ratio is 2, you have full occupancy of the tetrahedral sites of the lattice. So there are 8 tetrahedral sites and 4 metal atoms. And that is allowed within Swittendick criterion, which stipulates that the interhydrogen spacing should be no less than 2.1 angstroms. And in an FCC hydride where hydrogen metal ratio is 2.5, full occupancy of the tetrahedral sites and partial occupancy of the octahedral sites in the lattice occurs. This is not allowed from the Swittendick criterion, which has been corroborated many times. So why is this the case with our high entropy solutions? Well, there's one of two proposed methods for rationalizing this. So the first is based on the lattice distortion. Elements of different sizes result in an internal strain for the lattice, which increases the distance between these interstitial sites. So the size disparity of these atoms allows these sites to be occupied by the hydrogen, and that increases the inter-hydrogen distance to outwith the threshold stipulated by Swittendick, which allows for the simultaneous occupation of these sites. However, a recent proposal has come from electron localization. So based on the unique chemical environment that a solid solution offers, you have a less homogeneous localization of electrons versus elements. So for example, here we have a heat map, which shows electron density and localization. So these metal spheres, the metals are here in the blue, and the intermetallic bonds are less homogeneous with their distribution. You have more localization around the octahedral sites. This allows the hydrogen to be polarized when it occupies the octahedral site, which reduces the hydrogen-hydrogen repulsion, and that increases the stability of the octahedral site. So this isn't to say that one method is true or the other. This is more of an invitation to discussion, if anything, as it's very unclear as it stands which, if either or neither, are the more convincing method to rationalizing this. So I'd just like to take 2 minutes to thank everybody involved with this project, particularly my supervisors at Queen Mary's and the ICMPE, Dr. Jalagi, who's now based in Oslo, Professor Mike Rees and Claudia Zlatea, my bosses, and also my funders at DSTL, and my contacts there, Jitu Patel and David Holland-Smith. And if there are any questions, I look forward to answering them.
Thanks, Aaron. Next up is Dr. Efstathios Tingas. He's a lecturer at Edinburgh Napier University. He received his degree in aeronautical science from the Hellenic Air Force Academy in Greece. He studied PhD in mechanics from the National Technical University of Athens. And before his current appointment, he was an aircraft engineer with speciality in jet engines for the Hellenic Air Force, and a postdoctoral research associate at Coast, and a lecturer in engineering and aviation at Perth College. So over to you, Efstathios.
Okay, so good afternoon all. My name is Efstathios Tingas, and I will talk to you about a recent collaborative work between Edinburgh Napier University and University of Glasgow, which is a computational study about a novel zero-carbon hydrogen-fueled thermal engine for heavy-duty transport applications. In a nutshell, the overarching aim of this project was to perform a feasibility study using simplified numerical models of a new zero-carbon hydrogen-based technology that will allow the fast decarbonization of trucks and ships. I will firstly talk about the motivation of this work, then I will briefly highlight the individual objectives, and next I plan to dedicate most of the time discussing the methods we used and, most important, the results we obtained from this study. So the decarbonization of these applications through electrification has not been very attractive so far, and there are many reasons for that. One question that can naturally rise is, can we use hydrogen to decarbonize these heavy-duty transport applications, ideally through retrofitting? Now, both ships and trucks are predominantly powered with compression ignition engines, and there are many challenges in using hydrogen in compression ignition engines, but probably the most important is that simply hydrogen does not ignite because of hydrogen's very high autoignition temperature. Three strategies have been proposed so far to tackle this. The first one is to use very high compression ratios, above 30, compared to the range of 15 to 20 that conventional compression ignition engines currently operate. This basically means engine redesign, which is not very cost effective. The second approach is to use a glow plug to preheat the in-cylinder air or charge. This is not actually a bad idea, but the preheating creates several implications. Probably the most important is that it leads to the decrease of the engine performance and to high NOx. The last approach is to use a small quantity of a second fuel, typically called the pilot fuel, which is more reactive than hydrogen, in order to initiate the ignition. And there are many benefits with this approach. One is the flexibility in operation, increased efficiency, and others. But so far, only carbon-based fuels. In fact, most of the times it has been diesel that were used in that role. One non-carbon-based fuel that can be used as an ignition promoter for this purpose, that is also already available in the market, is hydrogen peroxide. It can be produced from renewable sources and can be found in any convenience store or supermarket in diluted form, diluted in water. The idea of using hydrogen peroxide in combustion is not actually new. It dates back to the 1940s, when it was first used as a rocket propellant and fuel for submarines. But apart from the military and aerospace applications where it is used even nowadays, it has also been used in transport-related applications. There, it has been used as an ignition promoter, just like we propose in the current project. So what we propose is the use of hydrogen peroxide as an ignition promoter to enable the use of hydrogen in compression ignition mode. We also consider water dilution for two reasons. Firstly, because hydrogen peroxide would most probably need to be diluted in water anyway. And secondly, because water dilution is an established method for reducing NOx emissions and mitigating abnormal combustion, like NOx. Our investigation included both HCCI mode and the more conventional compression ignition mode, and focused on engine performance characteristics, combustion phasing, and NOx under various conditions. We also aimed to touch on the limitations by abnormal combustion as manifested by increased pressurized rates, and provide some insight on the available injection strategies. Now, starting with the HCCI mode, there we used a zero-dimensional single-zone HCCI model available in the Chemking Pro suite in ANSYS. The engine cylinder specifications, typical of a conventional compression ignition engine, are shown in the current table. One thing to note is that although we investigated a range of compression ratios, in the following I will only discuss results for the case of compression ratio equal to 17. Another point to highlight is that the conventional definition of the equivalence ratio is no longer valid. So we have been using an effective equivalence ratio defined as shown here in the slide. This is an important point because the introduction of peroxide and water are both performed while maintaining the effective equivalence ratio constant. Now, on a mass basis, the energy density of hydrogen is much higher. It's actually 40 times higher than hydrogen peroxides. However, on a volume basis, hydrogen peroxide has an energy density which is more than 400 times larger than the energy density of hydrogen. Since the addition of peroxide is performed on a volume basis, it is reasonable to expect that the addition of peroxide will lead to the increase of the volumetric energy density of the mixture. At the same time, it is expected that the gravimetric energy density of the mixture will drop with the addition of peroxide. The results presented in the figure on the left confirm indeed these expected trends. The figure on the right also underlines the strong influence of the hydrogen peroxide addition on the volumetric energy density. There we can see that with merely 2% of hydrogen peroxide addition per volume basis, 90% of the volumetric energy density is due to the peroxide, which is not surprising given the significantly higher volumetric energy density of the hydrogen peroxide. For the HCCI mode, I have organized the results in two sections. In the first, we'll only consider hydrogen and hydrogen peroxide mixtures. In the second section, steam dilution is also added on top of hydrogen and hydrogen peroxide. Now, the investigation was performed in a range of equivalence ratios and engine speeds. Each case of hydrogen peroxide addition is compared against the respective glow plug approach, which means we remove the hydrogen peroxide and properly increase the inlet temperature. For a fair comparison, we ensure that the ignition occurs at exactly the same crank angle degrees between the two cases. For example, at phi equal to 0.1 and 1000 RPM, we use 12% hydrogen peroxide to achieve an ignition crank angle equal to 1.9 roughly degrees. And in order to achieve the same outcome without any peroxide, we had to increase the inlet temperature to 386 Kelvin. You can clearly see that when hydrogen peroxide is added, IMEP, torque, and power all increase substantially. Thermal efficiency also increases, but not that much, and NOx decrease significantly. In summary, the comparison against the glow plug approach reveals that as the mixture becomes richer, firstly, the required peroxide addition to achieve ignition at roughly 2 degrees decreases substantially. Secondly, IMEP, power, and torque all increase significantly with the addition of peroxide, but as the mixture becomes richer, their increase drops. On the other hand, hydrogen peroxide addition also affects thermal efficiency and NOx, but as the mixture becomes richer, its impact remains unaffected, in that thermal efficiency only slightly increases and NOx decrease substantially. Now, the results already discussed provide us insight on what to expect when we are investigating the incremental increase of hydrogen peroxide content at the initial mixture. So, in terms of the ignition CAD, the ignition crank angle degrees, the addition of peroxide results initially demonstrate drastic reduction of the ignition CAD, and further addition has negligible effect on the ignition promotion. Therefore, the ignition CAD actually levels off. This profile becomes attenuated at very lean conditions, that is with phi equal to 0.1. And in fact, as the engine speed increases, the dependence of ignition CAD on the peroxide becomes roughly linear. In essence, as the mixture becomes richer and regardless the engine speed, the effect of hydrogen peroxide addition on the ignition promotion becomes more pronounced. In terms of IMEP, the increase that peroxide induces seems to be mostly linear. If we were to look at the gradients of these profiles as a measure to assess the sensitivity of IMEP to the peroxide addition, we would find out that as the mixture becomes richer, hydrogen peroxide addition results in stronger impact. So the gradients become steeper, but the rate of this change becomes smaller. So from the first part of the investigation of the HCCI mode, let's now add steam dilution into the system to see how this would work. Similar to the earlier scenario, we compare our approach against that of a glow plug in terms of performance and NOx. So for each case of hydrogen peroxide addition, we run another without any peroxide, but having properly increased the inlet temperature to achieve the same ignition CAD. Unlike the previous scenario, we are now considering steam dilution. So for instance, at phi equal to 0.5, 3000 RPM and 10% water dilution, we need 7.3 hydrogen peroxide to achieve ignition at 5 degrees. But if we remove the peroxide we would need to increase the inlet temperature at 393 Kelvin to achieve the same ignition delay time. You can clearly see that with the proposed approach, that is with the addition of hydrogen peroxide, IMAP, torque both increase significantly, while NOx production decreases greatly. Now, 3 points I would like to make here about the peroxide strategy. Firstly, it results in notably higher engine performance values between 16 and 39% in view of IMAP power and torque. The difference between the two approaches in view of these metrics is favored as steam dilution or effective equivalence ratio increase. In either case, the achieved enhancement is the result of the mixture's higher energy density. Secondly, peroxide addition produces a negligible improvement in the thermal efficiency, roughly 2%, which is generally favored as the effective equivalence ratio or the steam dilution increase. Thirdly, peroxide addition induces a remarkable decrease between 50 and 76% of NOx emissions, reaching values of less than 100 ppm VD, while also maintaining high load. This decrease is generally inversely proportional to the steam dilution level and the effective equivalence ratio. Staying a little further in comparison against the glow plug approach, what we did next was to first consider heat losses, and secondly, to keep fixed the hydrogen peroxide content at 5%, and then add incrementally steam dilution into the system from 0 to 10%. Then we removed the hydrogen peroxide and tried to reproduce the same load output, the same power output, by properly increasing the inlet temperature. And the result in terms of IMAP and torque is shown in the figure on the left. In most cases, increasing the inlet temperature was not actually sufficient, so we also properly increased the equivalence ratio additionally, and this is shown in the figure in the middle here. For instance, to achieve an IMAP value of 7.4 with 6% of steam dilution, with hydrogen peroxide, we achieved that by adding 5% at V equal to 0.4. But with the glow plug approach, we had to increase the inlet temperature to 376 Kelvin and the equivalence ratio to 0.535, which is a 34% increase. The figure on the right compares the two approaches in view of thermal efficiency and NOx emissions, and the benefits of the use of peroxide are showcased again. In fact, as steam dilution increases, the decrease in NOx increases and reaches 2 orders of magnitude difference. What's also interesting is that thermal efficiency is also significantly affected, and the difference between the two approaches becomes more pronounced, mainly because of the increase of the fuel mass in the case where no hydrogen peroxide is used. Next, we consider the effect of both hydrogen peroxide addition and steam dilution on IMAP and NOx emissions. The x-axis represents the peroxide addition and the y-axis denotes the steam dilution. We are interested in the areas where NOx are low, that is red color, and IMAP is high, and that is purple. Generally, both IMAP and NOx increase with the addition of peroxide and decrease with the steam dilution increase. So at 1000 RPM, where phi is equal to 0.3, we can see basically that NOx are low for all conditions, except perhaps for hydrogen peroxide higher than 15%, and steam dilution is less than 3%. So an IMAP of 6 bar can very well be reached with 10% peroxide and 5% steam dilution while maintaining NOx extremely low. At 2000 RPM and phi equal to 0.4, an IMAP of 10 bar can very well be obtained with 10% peroxide addition again and 5% steam dilution, while again keeping NOx very low at around 100 ppm. These results showcase that steam dilution can indeed be an effective tool of reducing significantly NOx emissions while also achieving good load outcomes with no more than 10% of hydrogen peroxide. The second part of the study focused on a conventional dual-fuel compression ignition mode. Unlike the HCCI mode, where we employed an already available engine model, for the conventional dual-fuel compression ignition mode, a new engine model was developed from scratch. Now, due to the novelty of the developed model, I will spend some time presenting the steps we followed, as well as its structure, before then moving to the results. A zero-dimensional, time-dependent engine model was developed. In principle, the model integrates in time the equations of pressure, volume, heat, and the mass burn fraction, the latter being the Weibe function, which also controls the heat of combustion. The Weibe function is an empirical relation which makes use of two constants, C1 and C2. The values of these two constants have been tested against various carbon-based fuels, and in many cases, they take the values of 5 and 3 respectively. However, we could not find any literature for hydrogen. So the main task in the development of the new model was to determine values, or as you will see next, expressions for the two constants C1 and C2, along with the start of combustion and the combustion duration. A series of chemical simulations generated combustion data for hydrogen and hydrogen peroxide solution mixtures under the HCCI mode. Using results from these simulations, we were able to determine the mass burn fraction and hence the start of combustion and the combustion duration. Then, by linearizing the expression of the Weibe function, we can determine the approximate values for the two constants, C1 and C2, for each engine cycle by performing a linear regression on data points taken from the mass burn fraction generated from the kinetic simulation. An example comparing the mass burn fraction derived from a kinetic simulation with its representative Weibe function is presented in the figure on the left. The profile of the mass burn fraction curve is dependent on the mixture's initial conditions, and particularly the initial content of the hydrogen peroxide, as it is displayed in the figure on the right. Now, to account for this variability, the parameters of the Weibe function need to be adjusted accordingly, and following the aforementioned approach, some good accuracy could be obtained, as it is illustrated in the figure on the right. To tackle this behavior, a strategy of using adaptive Weibe function parameters was implemented. Correlations for each parameter were established as the peroxide solution injection ratio increased at given concentrations and equivalence ratios. These correlations were ultimately calculated in terms of the peroxide molar fraction in the reacting mixture. The figure on the right also shows the fitting that was applied on the available data in order to determine the correlation of the combustion duration as a function of the peroxide content. A range of simulations were executed to determine the effect of injection timing and injection duration in the engine cylinder. Equivalence ratio and the peroxide percentage, as well as the engine speed, were all maintained constant, while the injection start ranged between -20 up to 10 plus 10 crank angle degrees, and the injection interval ranged from 1 up to 25 degrees. In general, peroxide injections from -20 up to 3 CAD after top dead center generated high power output. Furthermore, an optimum injection timing appears to be between -8 and -9 crank angle degrees before the top dead center. Additionally, there appears to be a benefit to extending the injection duration beyond 10 crank angle degrees. A significant jump in the IMAP appears for all injection timings as the injection duration extends past the 10 crank angle degrees threshold. However, this effect appears to have diminishing results. The combustion initiated between -8 crank angle degrees timing provides the ideal pressure profile for maximizing the cycle work during the expansion stroke and thus improving IMAP. The figure on the left shows this effect since the rapid period of pressure rise is just after the piston top dead center, peaking at around 1.8 crank angle degrees after top dead center in this case, and ensuring the maximum cylinder pressure during the expansion stroke. In contrast, the zero CAD injection pressure profile develops well after the top dead center, losing out on around 10 crank angle degrees of net piston work at the start of the expansion stroke. Additional insight into this process can be obtained by examining the effect of the injection duration, as shown in the figure on the right. For the -8 crank angle degrees injection timing, the heat release rate profile for the longer injection durations tends to skew to the left, meaning the combustion heat in these cases is released earlier and faster than in the shorter duration. Finally, analysis of the model also illustrates the effect of the peroxide and hydrogen combustion has on the pressure rise in the cylinder. The analysis revealed that the pressure rise rate increases as the peroxide content of the mixture increases. It was also found that longer injection durations tend to reduce the high pressure rise rates, as does the later injection timing. All these preliminary findings reached through these investigations reveal that the proposed approach seems to be very promising, since firstly, it is clearly advantageous against the glow plug approach and the preheating of the charge. Secondly, the addition of peroxide results in the increase of YMAP and torque, while also greatly decreasing NOx. Thirdly, steam dilution could be an invaluable tool offering unique operational flexibility, since it can reduce tremendously NOx emissions. That, in combination with a balancing of the equivalence ratio, can require less than 10% of the peroxide, regardless the operational requirements. Now, one challenge that needs to be addressed and was highlighted in this work was that of the high pressure rise rates. For that, we believe that the use of the EGR or steam dilution combined with mixture stratification and the injection strategy will offer a realistic and effective solution. And with that, I would like to thank you for your attention and thank the network for the financial support.
Thank you, Stathis. We're going to move on quickly to our final presentation today. It's going to be given by Dr. Sumit Roy. He is an associate professor and fellow of Durham Energy Institute. He has a strong research track record in the area of renewable energies. His research focuses on decarbonisation of transport, hydrogen-based economy, renewable energy generation, electric vehicles, free piston engines, and modelling and simulation of complex systems. Over to you, Sumit.
Thank you so much, Tony. Good afternoon, everyone. My name is Sumit Roy, and today I'm going to talk about techno-economic assessment of fuel cell-ready hydrogen production by methane pyrolysis for transport applications. Over the last century, temperatures have risen as a direct result of drastically increased levels of greenhouse gases, such as carbon dioxide. Over 90% of this increase can be directly attributed to the combustion of fossil fuels, which produces CO2 with heat and water. The transport sector accounts for approximately 1/3 of the overall greenhouse gas emissions. To keep global temperatures below a 2-degree rise as per the Paris Agreement, sustainable and CO2 neutral energy resources must be researched and developed. Many pathways lead to hydrogen as an alternative fuel with a view to provide energy for transportation and industry, and to be used in highly efficient hydrogen fuel cells. The global hydrogen production market was valued at $136 billion in 2021, and it is expected to reach $219 billion by 2030. Over 95% of hydrogen produced today is made using technologies that are reliant on fossil fuels, of which most prevalent processes are CO2 emitting. Around 50% is made by steam methane reforming, which, although favorable, since it produces 4 moles of hydrogen for a mole of methane, but it also produces 1 mole of CO2, which offsets hydrogen's environmental benefits. This requires further investment for carbon capture, utilization, and storage. Also, the blue hydrogen produced from fossil fuels are not pure enough for fuel cells. On the other hand, water electrolysis, also known as green hydrogen, if powered by electricity derived from renewable sources, accounts for only 4% of hydrogen production. Also, hydrogen produced by the electrolysis is approximately 3.5 times more expensive. Methane pyrolysis is another way of producing hydrogen from methane. It is the thermal decomposition of methane into 2 moles of hydrogen and 1 mole of solid carbon. Since oxygen is not present in the reaction, carbon oxides cannot form, and thus there are no direct CO2 emissions from the process, putting methane pyrolysis at an advantage over other fossil fuel-based technologies. To this end, we modeled a pyrolysis reactor capable of producing 200 kiloton per annum of hydrogen. A liquid metal bubbling column reactor was designed with a porous plate distributor to maximize the surface area of conversion. It utilizes a molten nickel bismuth alloy as a catalyst, which remains stationary with the chamber, while the lower density molten salt, sodium bromide used here, is pumped in at the bottom of the reactor, transferring heat to the metal as it rises, settling above the metal. Sodium bromide was chosen because of its low cost and ability to be pumped at higher temperatures. This is tapped off along with the carbon product, which deposits on top of the salt as the bubble rises. Hydrogen and unreacted methane, approximately 12% of unreacted methane, are released through the top of the reactor. We modeled the operating conditions, and the optimal values recommended for the reactor was 1100 degrees centigrade at 20 bar pressure. I'm going to explain a simplified process flow sheet here. So preheated methane enters the pyrolysis reactor, which itself provided heat by the molten salt. The molten salt is heated either by a natural gas fired heater or an electric arc furnace. The hydrogen product leaves the reactor and is separated from any unreacted methane using a pressure swing adsorption unit, producing 99.999% of pure hydrogen. Parts gas from the PSA unit is primarily consisting of unreacted methane, is either recycled here or it can be burned in a steam cycle to generate electricity. Another small steam cycle recovers heat from the carbon product. 4 case scenarios for the plant operation have been considered, allowing a direct comparison between 2 heating methods. One was natural gas fired heater or electric arc furnace, and whether to burn the purge gas leaving the PSA unit. Shall we burn it to generate electricity in a steam cycle, or to recycle it in the system? So in the first case, we considered a natural gas fired heater to heat up the molten salt, and we considered burning the flue gas coming out of the pressure swing adsorption unit. In the second case, we instead of considering a natural gas fired heater, we considered an electric arc furnace heater, and we're still burning the unreacted methane in a steam cycle to generate electricity. That's case study 2. In the third and fourth, we are recycling the flue gases, and in the third case, we are using a natural gas fired heater. The fourth one is similar to the third one, except we are utilizing a electric arc furnace heater to heat up the molten salt. A thermodynamic analysis of the plant was conducted to compare the four scenarios. So the Sankey diagram shows the process heat flows of each case scenarios. This is case one, where we have natural gas fired heater with the flue gas burn in a steam cycle. Second one is again burning the flue gas with electric arc furnace. Third one is natural gas fired, where we are recycling the flue gas, and electric arc furnace with flue recycling is the fourth case. It is immediately clear that case one and case two, in which the purge gas from the pressure swing adsorption unit are combusted to raise the steam, are significantly higher consumers of methane as compared to the case three and case two. This is primarily because there is approximately 12% of unreacted methane coming out of the pyrolysis reactor, which is burned here. But instead, if we continuously recycle these purge gases such as in case 3 and case 4, which allows methane conversion up to 100%, this is shown by the hydrogen yield here, where in case 4 shows a hydrogen output of 2 moles for every 1 mole of methane, since this scenario does not consume methane elsewhere. The case 4 scenario is where we are using an electric arc furnace to heat up the molten salt, and we don't have the steam cycle here. We are recycling everything from the PSA unit in the cycle, so we consume 100% of the methane. So the process efficiency for these cases are 23.9%, 26.2%, 43.1%, and 50.1% respectively for case 1, 2, 3, and 4. The significant waste heat in cases 1 and 2 as a result of the typical thermal efficiency of electricity production using a steam cycle. That's why we are wasting more heat. Case 4 had the highest efficiency, 50.1%. Although case 3 uses a recycle setup like this, but instead of using an electric arc furnace, it utilizes a natural gas fired heater, which reduces the thermal efficiency as compared to case 4. That's why case 3 had 43% and case 4 had almost 50% efficiency. However, this means the case 4 also consumes more electricity compared to case 3, so case 3 has natural gas fired heater and case 4 has electric arc furnace. It is also clear that these comparisons, the Efstathios carbon capture and storage system should be employed for scenario 1 and 2 to reduce their environmental impact. But in case of case 4, there is no requirement of carbon capture and storage, as we are converting 100% of methane into hydrogen. An economic analysis was also conducted to compare the 4 cases. In table 4, listed for each case scenario are the bare erected cost, capital expenditure, and operating expenditure, along with levelized cost of hydrogen. The figures on the right represent the split of bare expenditure cost. The impact of electricity production using a steam cycle on bare erected cost can be evident in case 1 and case 2, where we used a steam cycle to generate electricity, where we are not recycling the purge gas from the pressure swing adsorption. In case 1 and case 2, steam cycle can be seen to make up around 30% of the total bare erected cost, where in figure 3 and 4, it is roughly half for that of case 3 and 4. The operating expenditure for methane pyrolysis plant was found to be between $198 million per year to $390 million per year, which was dominated by 4 factors, primarily price of methane, price of electricity, the carbon tax, and the sale value of solid carbon black. The levelized cost of hydrogen was found to be $1.29 per kg for the most cost-effective design, which was design 4, where we are using an electric arc furnace and we are recycling the purge gas from the pressure swing adsorption unit. These results show case